Welcome to the Reinforcement Learning Jumpstart series. I'm your host, Phil Tabor. If you don't know me, I'm a physicist and former semiconductor engineer turned machine learning practitioner. In this series of tutorials, you're going to learn everything you need to know to get started with reinforcement learning. You don't need any prior exposure. All you really need is some basic familiarity with Python. As far as requirements for this course, they are pretty light. You will need the OpenAI Gym because we're going to be taking advantage of that rather extensively. You'll also need the Atari extension for that so we can play games like Breakout, Space Invaders. You'll also need the Box 2D extension so we can do the Lunar Lander environment. And beyond that, you will need the Tensorflow library as well as PyTorch. And I'm going to have tutorials in both Tensorflow and PyTorch with a bit of a stronger emphasis on Tensorflow. I'm going to teach a course in somewhat of a top-down fashion, meaning we're going to get to the really important and exciting new stuff like DBQ Learning and policy gradient methods first. After that, we'll kind of back up and take a look at things like SARSA, Qlearning, and we'll even get into how to make your own reinforcement learning environments when we code up our own grid world and then solve it with regular Qlearning. If you missed something in the code, don't worry. I keep all of this code on my GitHub, which I will link in the pinned comment down below. I'll also link the relevant timestamps for all the material in case you want to jump around because maybe some topics interest you more or you want to get some additional background information from the explainer videos. Questions, comments, leave them down below. I will address all of them. Let's get to it. In this video, you're going to learn everything you need to know to implement Qlearning from scratch. You don't need any prior exposure to Qlearning. You don't even really need much familiarity with reinforcement learning. You'll get everything you need in this video. If you're new here, I'm Phil, and I'm here to help you get started with machine learning. I upload 3 videos a week, so make sure to subscribe so you don't miss out. Imagine you've just gotten the recognition you deserve in the form of offers for a machine learning engineering position from Google, Facebook, and Amazon. All 3 are offering you a boatload of money, and your dreams of big balling are interrupted by the realization that starting salary is just, well, the starting salary. You've got friends in each of the 3 companies, so you reach out to find out about the promotion schedules with each. Facebook offers $250,000 to start with a 10% raise after 3 years, but with a 40% probability that you'll quit. Google offers $200,000 to start with a 20% raise after 3 years, but with only a 25% probability that you'll quit. Amazon offers $350,000 to start with a 5% raise after 5 years, with a 60% chance that you'll end up washing out. So which should you take? All 3 offer big money, but future raises are far from certain. This is the sort of problem reinforcement learning is designed to solve. How can an agent maximize long-term rewards in environments with uncertainties? Qlearning is a powerful solution because it lets agents learn from the environment in real time and quickly learn novel strategies for mastering the task at hand. Qlearning works by mapping pairs of states and actions to the future rewards the agent expects to receive. It decides which actions to take based on a strategy called Epsilon greedy action selection. Basically, the agent spends some time taking random actions to explore the environment and the remainder of the time selecting actions with the highest known expected future rewards. Epsilon refers to the fraction of the time the agent spends exploring, and it's a model hyperparameter between 0 and 1. You can gradually decrease epsilon over time to some finite value so that your agent eventually converges on a mostly greedy strategy. You probably don't want to set epsilon at 0 exactly, since it's important to always be testing the agent's model of the environment. After selecting and taking some action, the agent gets its reward from the environment. What sets Qlearning apart from many reinforcement learning algorithms is that it performs its learning operation after each time step instead of at the end of each episode, as is the case with policy gradient methods. At this point, it's important to make a distinction. Traditional Qlearning works by literally keeping a table of state and action pairs. If you're implementing this in Python, you could use a dictionary with state and action tuples as keys. This is only feasible in environments with a limited number of discrete states and actions. Here, the agent doesn't need to keep track of its history since it can just update the table in place as it plays the game. The way the agent updates its memory is by taking the difference in expected returns between the actions it took with the action that had the highest possible future returns. This ends up biasing the agent's estimates over time towards the actions that end up producing the best possible outcomes. When we're dealing with environments that have a huge number of states or a state space that is continuous, then we really can't use a table. In that case, we have to use deep neural networks to take these observations of the environment and turn them into discrete outputs that correspond to the value of each action. This is called deep Qlearning. The reason we have to use neural networks is that they are universal function approximators. It turns out that deep neural nets can approximate any continuous function, which is precisely what we have. The relationship between states, actions, and future returns is a function that the agent wants to learn so it can maximize its future rewards. Deep Qlearning agents have a memory of the states they saw, the actions they took, and the rewards they received. During each learning step, the agent samples a subset of this memory to feed these states through its neural network and compute the values of the actions it took. Just like with regular Qlearning, the agent also computes the values for the maximal actions and uses the difference between the two as its loss function to update the weights of the neural network. So let's talk implementation. In practice, we end up with two deep neural networks. One network, called the evaluation network, is to evaluate the current state and see which action to take, and another network, called the target network, that is used to calculate the value of maximal actions during the learning step. The reasoning for why you need two networks is a little complicated, but basically it boils down to eliminating bias in the estimates of the values of the actions. The weights of the target network are periodically updated with the weights of the evaluation network so that the estimates of the maximal actions can get more accurate over time. If you're dealing with an environment that gives pixel images, just like in the Atari library from the OpenAI gym, then you will need to use a convolutional neural network to perform feature extraction on the images. The output from the convolutional network is flattened and then fed into a dense neural network to approximate the values of each action for your agent. If the environment has movement, as most do, then you have an additional problem to solve. If you take a look at this image, can you tell which way the ball or paddle is moving? It's pretty much impossible for you to get a sense of motion from just a single image, and this limitation applies to the deep Qlearning agent as well. This means you'll need a way of stacking frames to give the agent a sense of motion. So to be clear, this means that the convolutional neural network takes in the batch of stacked images as input rather than a single image. Choosing an action is reasonably straightforward. Generate a random number, and if it's less than the epsilon parameter, pick an action at random. If it's greater than the agent's epsilon, then feed the set of stacked frames through the evaluation network to get the values for all the actions in the current state. Find the maximal action and take it. Once you get the new state back from the environment, add it to the end of your stacked frames, and store the stacked frames, actions, and rewards in the agent's memory. Then, perform the learning operation by sampling the agent's memory. It's really important to get a non-sequential random sampling of the memory so that you avoid getting trapped in one little corner of parameter space. As long as you keep track of the state transitions, actions, and rewards in the same way, this should be pretty safe. Feed that random batch of data through the evaluation and target networks and then compute the loss function to perform your loss minimization step for the neural network. That's really all there is to deep Qlearning. A couple neural networks, a memory to keep track of states, and lots of GPU horsepower to handle the training. Speaking of which, of course, you'll need to pick a framework, preferably one that lets you use a GPU for the learning. PyTorch and Tensorflow are both great choices and both support model checkpointing. This will be critical if you have other stuff to do and can't dedicate a day or so for model training. That's it for now. Make sure to share the video if you found it helpful and subscribe so you don't miss any future reinforcement learning content. I'll see you in the next video. In this tutorial, you're going to learn how to use deep Qlearning to teach an agent to play Breakout in the Tensorflow framework. You don't need to know anything about deep Qlearning. You don't even need to know anything about Tensorflow. You just have to follow along. Let's get started. If you're new to the channel, I'm Phil, a physicist and former semiconductor engineer turned machine learning practitioner. Here at Machine Learning with Phil, we do deep reinforcement learning and artificial intelligence tutorials 3 times a week. So if you're into that kind of thing, hit that subscribe button. Let's get to the video. So if you're not familiar with deep Qlearning, the basic idea is that the agent uses a convolutional neural network to turn the set of images from the game into a set of feature vectors. Those are fed into a fully connected layer to determine the value of each of the actions given some set of states. In this case, a set of states is just going to be a stack of frames because we want the agent to have a sense of motion. So as we go along, we'll be stacking up frames, passing them into our network, and asking the network, hey, what is the value of either of the actions, move left, move right, or fire a ball? We're going to split this into 2 classes, one of which will house the DBQ networks and the other will house the agent. And in the agent class, we're going to have other stuff that we'll get to later. Let's go ahead and start with our imports. We'll need OS to handle model saving. We'll need numpy to handle some basic random functions. And of course, Tensorflow to build our agent. So we'll start with our DBQ network. The initializer is pretty straightforward. We're going to take the learning rate, number of actions, the name of the network. That is important because we're going to have two networks, one to select an action, one to tell us the value of an action. More on that later. The number of dimensions in the first fully connected layer. The input dimensions of our environment. So for the Atari gym, the Atari library of the OpenAI gym, all of the images have 210 by 160 resolution, and we're going to pass in a set of frames to give the agent a sense of motion. We're going to pass in 4 frames in particular, so it's going to be 210 by default, 210, 160 by 4. We're going to do some cropping later on. We'll get to that in a minute. We also need a directory to save our model. So the next thing we need is the TensorFlow session. This is what instantiates everything into the graph. And each network wants to have its own. Then we'll call the build network function to add everything to the graph. Once you've added everything to the graph, you have to initialize it. Very important. TensorFlow will complain if you don't do that, so best to do that now. And the way you do that is by calling the TF global variables initializer function. Other thing we need is a way of saving our models as we go along. And this is critical because this DBQ network takes forever to train. I let it train for about 10 hours and it averages a score of 2 to 3 points per set of whatever number of lives it gets. So it's going to have to train for quite some time, so we're going to want to be able to save it as we go along because we have other stuff to do, right? And of course, you want a way of saving your checkpoint files. Next thing we need is a way of keeping track of the parameters for each particular network. And you do that like this. So what this will do is tell TensorFlow that we want to keep track of all of the trainable variables for the network that corresponds to whatever the name of this particular network is. We use this later when we copy one network to another. Next, let's build our network. So we're going to encase everything in a scope that is based on the network's name. We're going to have placeholder variables that tell us the inputs to our model. We're going to want to input the stack of images from the Atari game. We want to input the actions that the agent took, as well as the target value for the Q network. We'll get to that in a minute. And this convention of naming placeholders and layers, you're going to see repeated throughout the TensorFlow library. The reason is that it makes debugging easier. If you get an error, it'll tell you the variable or layer that caused the error. Very handy. And so you can probably tell by the shape here that we are going to do a one-hot encoding of the actions. And the same thing for the Q target. So the convention of using none as the first parameter in the shape allows you to train a batch of stuff. And that's important because in virtually every deep learning application, you want to pass in a batch of information, right? In this case, we're going to be passing in batches of stacked frames. So we'll get to that in a moment. Next thing we have to do is start to build our, scroll down a little bit, start building our convolutional neural network. So let's start building our layers. The first one will have 32 filters, kernel size of 8 by 8, strides of 4, and a name of conv1. The other thing we need is an initializer. Now, we are going to use the initializer that the DeepMind team used in their paper. The reason is that we want to learn from the experts and may as well do what they do if it's going to make our life significantly easier. And that's going to be a variance scaling initializer with a scale of 2. And then we want to activate that with a ReLU function. Sorry, it's conv1 activated. So our next layer is pretty similar. It'll take the activated output of the first layer as input. That'll take 64 filters. If you're not familiar with what a filter is, you can check out my video on convolutional neural networks. A kernel size of, in this case, 4 by 4, strides of 2, name of conv2, and we can go ahead and copy that initializer. Why not? So that is our second convolutional layer, and we're going to do something similar for the third, of course. And that will take conv2 activated, 128 filters, 3 by 3 kernel. Good grief. A stride of 1 and a name of conv3. And the same initializer. And of course we want to activate it as well. So the next step is, once we have the outputs of our convolutional neural network, we want to flatten all of them and pass them through a dense network to get our Q values, or the values of each state action pair. Let's do that now. And that's where our FC1 DIMs come in. And we need a ReLU activation. And whoops, we will do the same initializer for the dense layer. So next up, we need to determine the Q values. Q in Qlearning just refers to the value of a state action pair. It's just the nomenclature. And this will be the output of our neural network. And of course we want to have one output for each action. And this gets the same initializer. Now we're not activating that yet. We want to just get the linear values, the linear activation of the output of our network. So the next thing we need is the actual value of Q for each action. And remember, actions is a placeholder. And next thing we need for every neural network is a loss function. So we just want to have the squared difference between the Q value that the network outputs and something called the Q target. The Q target, let's get to that now. So the way Qlearning works is that at each time step, it's a form of temporal difference learning. So every time step it learns and it says, hey, I took some action. What was the maximal action I could have taken? And then it takes the delta between whatever action it took and the maximal action, and uses that to update the neural network as its loss function. So our training operation is just a form of gradient descent, atom optimizer in this case. learning rate, and you want to minimize that loss function. Let's give this more room. So that is almost it. So that is our network. So the next thing we need is a way of saving files, right? And loading them as well. The reason we want this is, as we said, these models take a notoriously long time to train. And so we may want to start and stop as we go along. And what this will do is it will look in the checkpoint file and load up the graph from that file and save it, load it into the graph of the current session. And we're going to save frequently as we train, something like every 10 games. And all this function does is it takes the current session and outputs it to a file. Pretty handy. So that is our DBQ network. What this does, again, is it takes a batch of images from the environment, in this case breakout, passes it through convolutional neural network to do the feature selection, and then passes it through a fully connected layer to determine the value of each given action, and then uses the maximal value of the next action to determine its loss function and perform training on that network via backpropagation. Next up, we need an agent that includes everything else, all of the learning, all of the memories, all that good stuff. So it's going to take something called alpha, that is the learning rate. Gamma, that's a discount factor, a hyperparameter of our model. The memory size, number of actions, and epsilon, that determines how often it takes a random action. A batch size, a parameter that tells us how often we want to replace our target network. Set of input DIMMs, we use the same as before, 210, 160 by 4. One moment, my cat is whining. We need a directory to save the QNext network. And we will need a directory to save the QEvaluation. And what this, as I said, we'll have two networks, one that tells us the action to take and the other one that tells us the value of that action. So let's go ahead and start our initializer. So when we take random actions, we will need to know the action space, which is just the set of all possible actions. And we need to know the number of actions. We need our discount factor gamma. This tells the agent how much it wants to discount future rewards. The memory size, which tells us how many transitions to store in memory. Of course, our epsilon and epsilon greedy. And then we need our network to tell the agent the value of the next action. So we'll pass in the alpha learning rate, number of actions, input DIMMs, the name, and the checkpoint directory. Okay, so now we have our two networks. The next thing we need is a memory. So Qlearning works by saving the state, action, reward, and new state transitions in its memory. We're also going to save the terminal flags that tell the agent whether or not the game is done. That'll go into the calculation of our reward when we do the learning function. So we need a state memory, just a numpy array of zeros. We shape mem size and input DIMMs. And so this will save a set of 4 transitions, 4 frames, stacked 4 frames by number of memories. And we also need an action memory. And this will handle this will store the one-hot encoding of our actions. Now, that is just one-dimensional. This will just store the agent's memory of the rewards, and then we need the terminal memory. So this just saves the memory of the done flags. And to save RAM, we'll save that one as int 8. And you know what? We can do the same thing with the actions. And this is important because we're going to be saving 25,000 or so transitions. On my PC, this consumes about 47 gigabytes, 48 gigabytes of RAM. I have 96, so it fits. If you have less, you're going to need a significantly smaller memory size, just something to keep in mind. So next thing we need to do is to store those transitions in memory. And this is, of course, pretty straightforward. So we need the old state, the action, the reward, the new state, let's just call that state underscore, and a terminal flag. So that'll just be an integer 0 or 1. So the agent has some fixed memory size. We want to fill up to that memory, and then when we exceed it, we just want to go back to the beginning and start overriding it. So the index is just going to be mem counter, which is the something I forgot. Let's put that up here. So that will be the counter that keeps track of the number of memories that it has stored. So for our actions, we need to do the one-hot encoding. And when we pass in the action, it'll just be an integer. So making an array of zeros and setting the index of the action you took to 1 is a one-hot encoding. And of course, you want to increment the memory counter. So the next thing we need is a way of choosing actions. So DBQ Learning relies on what is called Epsilon greedy. So Epsilon is a parameter that tells it how often to choose a random action. We're going to decay Epsilon over time. The agent will start out acting purely randomly for many, many hundreds of games, and eventually the random factor will start decreasing over time, and the agent will take more and more greedy actions. A greedy action is choosing the action that has the highest value of the next state. So this takes the state as input. We need a random number from the numpy random number generator. And then we'll select an action at random from the agent's action space. If we are going to take a greedy action, then we need to actually find out what our next highest valued action is. So we need to use our evaluation network to run the qeval.qvalues tensor using a feed dict of the I can't talk and type at the same time, of the current state as the Q evaluation network input. And then, of course, if you want the maximum action, you just need numpy.argmax of actions. And when you're done, just return the action. So now we come to the meat of the problem. We have to handle the learning. So learning has many parts to it. The basic idea is, first thing we're going to do is check to see if we want to update the value of our target network. And if it's time to do that, we're going to go ahead and do that. The next thing we're going to do is select a batch of random memories. The most important thing here is that these memories are non-sequential. If you choose sequential memories, then the agent will get trapped in some little nook and cranny of parameter space, and what you'll get is oscillations in performance over time. To actually have robust learning, you want to select different transitions over the entirety of the memory. So that's how you handle memory batching and sampling. And then you have to calculate the value of the current action as well as the next maximum action. And then you plug that into the Bellman equation for the Qlearning algorithm and run your update function on your loss. So let's go ahead and do that. So first thing we want to do is see if it's time to replace our network, target network. If it is, go ahead and do that, and we'll write the update graph function momentarily. Next thing we want to do is find out where our memory ends. Less than mem size, else. This will allow us to randomly sample a subset of the memory. And this will give us a random choice in the range max mem of size batch size. So next we need our state batches. These are just the state transitions. We will need the actions we took, and remember we stored these as a one-hot encoding, so we need to go back to a integer encoding. So we need to handle that, and the simplest way to do that is just to do a numpy dot operation to just multiply two vectors together. So next we need to calculate the values of the current set of states as well as the set of next states. Sorry, we'll start with Qeval. And the next. So this will take the set of next states, the transitions. The next thing we want to do is copy the Qeval network, because we want the loss for all of the non-optimal actions to be 0. The next thing we need to do is calculate the value of Qtarget. So for all of these states in the batch, for the actions we actually took, plus this quantity here. So the maximum value of the next state multiplied by this quantity terminal batch. So the reason is that if the next state is the end of the episode, you just want to have the reward, whereas if it is not a terminal state, the next state, then you want to actually take into account the discounted future rewards. So next we need to feed all of this through our neural network. Through our training operation. We need the actions, which is the action we actually took, And we also need the target values, which we just calculated. So the next thing we need to do is to handle the prospect of decreasing epsilon over time. Remember, epsilon is the random factor that tells the agent how often to take a random action. The goal of learning is to eventually take the best possible actions. So you want to decrease that epsilon over time. So we handle that by allowing the agent to play some number of moves randomly. So we'll say 100,000 moves randomly. And we want to dictate some minimum value because you never want it to do purely greedy actions because you never know if your estimates are off. So you always want to be exploring to make sure your estimates are not off. And you can decrease epsilon over time any number of ways. You can do it linearly. That's what DeepMind did. You can use square roots. You can use any number of things. I'm just going to do this. We're going to multiply it by some fraction of 1. A bunch of 9s. That'll give you a really slow decrease of epsilon over time, so the agent takes a lot of random actions and does a lot of exploration. Sorry, I flipped my sign there. Thought that didn't look right. So yeah, if it tries to drop below 0.01, we're going to go ahead and set it there. Okay, so that is the learning function. Next up, we have to handle the functions to save the models. And this we'll just call the save checkpoint function for the respective networks. Next function we need is a way of updating our graph. So what we want to do is we want to copy the evaluation network to the target network. And this is actually a little bit tricky. So what you want are the target parameters. This is why we saved them earlier. And you want to perform a copy operation on them. Now, the reason this is non-trivial is because you have to pass in a session, and the decision of which session to use is non-trivial. So you have to use the session for the values that you're trying to copy from, not copy to. So if you had Q next, you would get an error, which took me a little bit to figure out. So that is our agent class. Next up, we have to code a main function. So of course we have to start again with our imports. We're going to import Jim, and we want to import a network. We will also need numpy to handle the reshaping of the observation. We're going to truncate it to make the workload on the GPU a little bit lower. So import numpy as np. If you want to save the games, you can actually use that with you can do that with the wrappers. So I won't put that in here, but I will put that in my GitHub version. So you can just do a git pull on this and you will have the way of saving the games. So first thing we have to do is pre-process our observations. And the reason you want to do this is because you don't need all of the image, we don't need the score, and we also don't need color. We just need one channel. So I've already figured it out. If you take row 30 onward and all the columns, then you will get a good image. And you want to reshape it like so. The next thing you have to handle is a way of stacking the frames. This is because the agent can't get a sense of motion by looking at only one picture, right? Nobody can get a sense of motion from looking at one picture. Worse yet, the OpenAI Atari library returns a sequence of frames where it could be a random number between 2, 3, or 4. So to get a sense of motion, we have to actually stack a set of frames, and we're going to handle that with this function. So we'll just keep a running stack of frames, the current frame to save, and the buffer size, which just tells you how many frames to save. So at the top of the episode, you're not going to have anything to save, right? There will be no stacked frames. So you want to initialize it. So it'll be the buffer size by the shape of each individual frame. Next, you want to iterate over that. And say each row, which corresponds to each image in your stack, gets assigned to a frame. So otherwise, it's not the beginning of the episode, and you want to pop off the bottom observation, shift the set of frames down, and append the new observation to the end. So instead of 1, 2, 3, 4, it'll be 2, 3, 4, and then frame 5. So let's do that. Equals, 0 to buffer size, -1. So this will shift everything down. And this will append the current frame to the end of the stack. Next, we have to do a reshape. And this is basically to make everything play nicely with the neural network. All right, now we're ready for our main function. Let's go ahead and save. Scroll down. Good grief. Breakout v0 is the name of the environment. This is just a flag to determine if we want to load a checkpoint. Sorry, so yeah, Epsilon starts out at 1.0, so the agent takes purely random actions. Our learning rate alpha will be something small like 0.00025, and we've reshaped our input so it needs to be 180 instead of 210, 180 by 160 by 4 because we're going to stack 4 frames. The breakout game has 3 actions and a memory size of 25,000, which, as I said, takes about 48 gigabytes of RAM. So go ahead and scale that based on however much you have. If you have 16 gigs, go ahead and reduce it down to something like 6,000 or 7,000. So the batch size tells us how many batches of memories to include for our training. We'll use 32. If load checkpoint is true, then we want to load the models. Next thing we need is a way of keeping track of the scores. We will need a parameter for the number of games. Stick with 200 to start with, a stack size of 4, and an initial score of 0. So the memory is originally initialized with a bunch of zeros. That is perfectly acceptable, but another option, something else we can do, is we can overwrite those zeros with actual gameplay sampled from the environment. So why don't we do that? And the actions are just chosen randomly, right? It's just to give the agent some idea of what is going on in the environment. So you want to reset at the top of every episode. You want to pre-process that observation. You want to go ahead and stack the frames. And then play your episode. So there's a bit of a quirk here. The agent saves its actions as 0, 1, or 2, but the actions in the environment are actually 1, 2, and 3. So we have to sample from that interval and then add 1, take the action, subtract 1, and then save the transition in the memory. Just a bit of a kludge, not a big problem. So then we want to add that to our stack. Go ahead and subtract off 1 from the action and store that transition in memory. And then finally set the old observation to be the new one. Let's go ahead and use a print statement. Okay, now that we've loaded up our agent with random memories, we can actually go ahead and play the game. One thing I like to do is print out the running average of the last 10 games so that we get an idea of if the agent is learning over time or not. You do it like this. And then just print that out. And I also like to know if Epsilon is still 1 or if it has actually started to decrease over time. And we also want to save the models every 10 games. And if on any other game we just want to print out the episode number and the score. So we can actually scroll up here, copy this. So we're not done. Whoops. There we go. So instead of a random choice, it is agent.chooseAction, and that takes in the observation. Oh, but we did forget to do the same thing here. Grab those and put them there. So the top of every episode, we reset the environment, pre-process the observation, and stack the frames. Quite critical. So we still have to do the same thing with adding and subtracting 1. We want to save the transitions, and the only other difference is that we want to learn at every step. And at the end of the episode, we want to go ahead and append our score, so that way we can keep track of our average. And if you want to get fancy, you can go ahead and add in a plotting function so that when this is done learning, you can plot the learning over time, and you should see an upward slope over time. And if you want to plot the epsilons, you should see a gradual downward slope as well. So I'm going to leave it here because the model is still training on my computer. It's run about 3,000 iterations, 3,000 games that is, and at best, it gets 2 to 3 points per set of 5 lives. So it's really going to need a couple days of training to get up to anything resembling competitive gameplay. But once it's done, I'll upload another video that explains how Qlearning works in depth and in detail, and I'll include the performance from this particular model in that video so you can check it out then. Feel free to run this yourself. When I finish the model, I will go ahead and upload the trained version to my GitHub, so you are free to download it if you don't have any decent GPUs to train this with. Go ahead, leave a comment down below, subscribe. I will see you all in the next video. Welcome back, everybody. In this series of videos, we're going to code up a DBQ network in PyTorch to play Space Invaders from the Atari OpenAI Gym library. In this first video, we're going to code the Convolutional Neural Network class. In the second video, we'll code up the agent class itself. And in the third, we'll get to coding the main loop and seeing how it all performs. Let's get to it. So if you're not familiar with the DBQ network, I would advise you to check out my earlier video, Bite-Sized Machine Learning, What is a DBQ Network? It's a quick little explainer video that gives you the gist of it within about 4.5 minutes. If you already know, then great, we're ready to rock and roll. But if you don't, I'll give you the brief. Too long didn't read. So basic idea is that we want to reduce some rather large state space into something more manageable. So we're going to use a convolutional neural network to reduce the representation of our state space into something more manageable, and that'll be fed into a fully connected neural network to compute the Q values, in other words, the action values for any particular given state. We're going to leverage two different networks, a network that is going to tell us the value of the current state, as well as a network to tell us the value of the successor states. This is going to be used to calculate the values of the target, and which is the purely greedy action, as well as the behavioral network, which is the current predicted state. And the difference between those two is used in the loss function for our stochastic gradient descent or root mean squared propagator. So let's go ahead and get started. We're going to start as usual by doing our imports. And there are quite a few in PyTorch. Great library. One thing I really like about it is that it's highly expressive. You don't have a whole lot of boilerplate code as you do in something like TensorFlow. TensorFlow is enormously powerful. And if you want to do cross-app type of software, then that's going to be really your only choice. For our purposes, this is going to be precisely what we want to use. And of course, numpy. So we're going to define a class for our DBQ network, and that'll derive from an n.module. This is kind of how PyTorch handles everything. You want to derive your class from the module, the base module, so that way you get access to all of the goodies. And we'll pass in our learning rate alpha for our stochastic gradient descent algorithm. All right, so the network is comprised of 3 convolutional layers and 2 fully connected layers. So the first one is just going to be a 2-dimensional convolution that's going to take 1 input channel. The reason is that the agent doesn't really care about color, so we're going to go ahead and make things easier, reduce our computational requirements by going to a grayscale representation. We'll take 32 filters with an 8x8 kernel, a stride of 4, and a padding of 1. Second layer is going to be pretty similar. This one, of course, will take 32 channels in, give 64 channels out, and do a 4x4 kernel with a stride of 2. And our third convolutional layer is going to be, of course, 2-dimensional as well. It takes in 64, outputs 128 with a 3x3 kernel. That's it for the convolutions. Hey, if you don't know how a convolutional neural network works, I'm going to go ahead and link a video here that will give you the basic idea of how those work. And if you would rather see how this stuff works in text form, I don't know if I mentioned this earlier, but there was an associated blog article on my website, neuralnet.ai. Yeah, I bought that domain. I'll link it in the description. Go ahead and check it out, please. So our fully connected layer is the following. And we're going to have to do a little bit of magic here. So after running this stuff a bunch of times, I know the dimensionality of the images of the convolutions we're going to get out. And what we want to know is we're going to be taking a set of filters, convolved images that have had filters applied to them, 128 to be exact. And we want to unroll them into a single flattened image, right, to feed into our neural network. So that's going to be 128 channels that are 19x8 in size. And that's a magic number I got from just by running the code and trial and error. And then our output layer is going to take in those 512 units and output 6. Why 6? That's because we have a total of 6 actions. In the game of Space Invaders, you have a total of 6 actions, which are the subset of the full 20 available in the Atari library. Basically, the agent can do nothing. It can move left, it can move right, it can shoot while standing still, and it can move left and right and shoot. When we get to the main video, I'll go ahead and show all those actions. We also need an optimizer equals optim RMS prop, and we want to tell it to take the parameters of our object for the weights. And our learning rate is going to be alpha that we've passed in. Our loss function is going to be a mean square error loss. And the components of that will be the target and the current predicted Q functions. And of course, the target is just the greedy value, right? Because Qlearning is an off-policy method that uses a Epsilon greedy behavioral policy to update the purely greedy target policy. Other thing we have to do in PyTorch is tell it which device we're using. So t.device, and that'll be CUDA 0 if t.CUDA is available, else CPU. And what this is telling it is that if the GPU is available, go ahead and use it, which is of course always preferable. Otherwise, just use the CPU. And we also have to tell it to actually send the network to the device. Maybe I'm using 0.4. I don't know if in 1.0 that's actually required, but as of the time I'm coding this up, it's required. So something we have to live with. Okay, so this is the sum and the whole of our network. Only thing that remains to do is to feed forward our observation. And that will take the observation. Not only can I not type, I cannot speak as well. I suck at life. I don't know why you guys listen to me. So what we want to do is the observation vector is we're going to use a sequence of frames, and those frames are the reduced images from the screen. So when we get to the third video on actually playing the game, you'll see that you don't need the full frame to actually figure out what's going on. You can actually truncate it to get a really good idea. In particular, the agent can only move left and right a certain amount, so we go ahead and truncate the sides. You don't need the score at the top because we're keeping track of the score ourselves, and you don't need some at the bottom. So you can actually truncate the image a little bit to reduce your memory requirements, and we're going to convert it into a grayscale. So we get rid of two. We're just going to average the 3 channels to make them into 1. And we also have to pass in a sequence of frames, right? Because if I only show you 1 frame of a video game, you can't tell what's going on. You don't get a sense of motion from a single frame, right? You need at least 2 to get a sense of motion. We'll be using 3, I believe, in the original implementation of this algorithm. For DeepMind, they used 4. We're going to go ahead and use 3 just to be different. I suspect that's a hyperparameter. It's not something I've played with. I encourage you to do that. Oh, another thing is that we must train this on a GPU. If you try to do it on your CPU, it's going to take 7,000 years. So if you do not have access to a GPU, go ahead and leave a comment below, and I will find a way to get my pre-trained model to you so you can go ahead and play around with this. I have a 1080 Ti, not top of the line anymore, but it's still quite good for this particular application. So back to the topic, we have to convert our sequence of frames, our observation, to a tensor, and we also want to send that to the device. This is a peculiarity of PyTorch. As far as I'm aware, I'm not the world's leading expert, but as far as I understand it, you have to tell it to send the network as well as the variables to the device as well. Not a big deal, just something to be aware of. Next thing we have to do is resize it. So when you are given a sequence of frames in the OpenAI gym, and really any other format of image is going to be height and width by channels. Whereas if you look up here, this actually expects the channels to come first. And so we have to reshape the array to accommodate that. So PyTorch's built-in function for that is view. We want a -1 to handle any number of stacked frames, 1 channel in the beginning, and we're going to pass in 185 by 195 image. That doesn't seem right, actually. Sorry, it's not 195. I'm like, the original image is 210 by 160. It can't be 185 by 195. Total brain fart there. It's 185 by 95. Okay, so we have taken in our sequence of frames. We've converted it into a tensor and converted it into the proper shape for our network. The next thing we want to do is activate it and feed it forward. So we call the first convolutional layer on our observation, and we use the relu function to activate it. And we store that in the new variable observation. And then we learn how to type, and then we do the same thing with that output. Pass it through the second convolutional layer. And then we do the same thing again. We pass it through the third convolutional layer. And we're almost home free. So the next thing we have to do is we are outputting a 128 by 19 by 8 set of arrays. The next thing we have to do is, oh, by the way, that noise was my Pomodoro timer. If you're not using the Pomodoro technique, I highly recommend it. It's an enormous productivity hack. But anyway, next thing we have to do is take our sequence of convolved images and flatten them to feed into our fully connected neural network. So we again use the view function to do that. -1 for whatever number of frames we pass in. 19 by 8 is what we get out, and I found that out through experimentation. And we know it's 128 channels because we dictate that here, right here, 128 output channels. So boom, we flattened it, and the only thing that remains is to feed it forward. And we'll use a relu activation function there, FC1, fully connected layer 1. And then it's not observation, but it's actions, self.fc2 observation. So we'll feed it through the final fully convolved layer and store that as a variable called actions and go ahead and return it. And the reason we're doing that is because what we're getting out is a Q value for each of our actions, and we want to pass that back. Now, keep in mind that we're passing in a sequence of frames, and so what we're going to get back is a matrix. It's not going to be a single array of 6 values. It's going to be 6 values times whatever number of rows of images you pass in. So if we pass in 3 images, it's going to have 3 rows and 6 columns, and that'll be important later when we actually get to choosing the actions. Speaking of which, I'm going to cut it short here. I've already rambled for about 12, 13 minutes. In part 2, we're going to take a look at coding up the agent class. I have structured it this way because the agent actually has 2 networks, so it made sense to kind of stick the network in its own class. We'll get to coding up the agent's init function, how to handle its memory, how to store transitions, how to choose actions, and how to actually implement the learning function. That's a much longer project, so we'll stick that in its own video. And then in part 3, we're going to get to actually coding up the main loop and seeing how it performs. Hey, if you like the video, make sure to like the video. Hey, if you don't like it, go ahead and hit the thumbs down. I don't really care. Let me know what you think. Questions, comments, leave them down below. If you made it this far, please consider subscribing. I look forward to seeing all of you in the next video. Welcome back, everybody. In the previous video, we got to coding the convolutional neural network class for our deep Qlearning agent that's going to play Space Invaders. If you haven't seen that yet, go ahead and click the link to go ahead and watch that first. Otherwise, you probably won't know what's going on. If you're the type of person that would prefer to have a written set of instructions, go ahead and click the link down below. I'll link to the associated blog article for this particular tutorial series. When we last left off, we just finished returning the set of actions, which is the set of Q values for our sequence of frames. So, of course, in this video, we're going to go ahead and get started coding up the agent class, which is where all the magic is going to happen. And of course, as always, I have left the code for this in my GitHub under the YouTube directory. It gets its own directory because there's a few different files here. I'll link that below as well. And if you aren't following me on GitHub, you probably should, because that's where I post all of my stuff. Okay, next up we have the agent class, right? And this is just going to derive from the base object class, nothing fancy here. We need a basic init function, and this is going to take gamma, which is our discount factor. So the agent has a choice of how to value future rewards. In general, it gets discounted by some value because a reward now is worth more than a reward in the future. Just like with us, we need epsilon for our epsilon greedy action selection, the alpha for the learning rate, the max memory size, a variable to keep track of how low we want epsilon to go, something to keep track of how long we replace, of how often we're going to replace our target network. I'll get to that in a moment, or in a few minutes. And the action space, and that's just a list of variables from 0 through 5. Those correspond to all the possible actions for our agent. And you just set these to the appropriate variables. Being careful not to turn on your caps lock key. So what these all are just hyperparameters for our agent. We don't need to store alpha because we're just going to pass that into the network and then never touch it again. Storing the action space allows us to accommodate the epsilon greedy action selection later. The mem size is used for efficiency purposes. So we're going to keep track of state, action, reward transitions. You don't want to store an infinite number of them. You only want to store a subset. You don't need to store all of them anyway. There's no real practical benefit since we're just sampling a subset anyway. So we just use some rather large memory to keep track of all of the state transitions that we care about. Keep track of how many steps, and the learn step counter, that is to keep track of how many times the agent has called the learn function. That is used for target network replacement. If you're not familiar with it, target network replacement is when you swap the parameters from the evaluation network to the target network. My experience has been that it doesn't actually help things, so I'm not going to do it. I'm going to code it in because it's an important part of the topic, but in this particular case, I haven't found it to be helpful. But I haven't played with it too much. I saw that it does quite well without it, so why break it? So I'm going to store the memory as a list, and the reason I'll use a list instead of a numpy array is because the associated cost of stacking numpy arrays is really, really high. So it's much, much faster to store a list of lists and then convert to a numpy array when you learn. And that's much faster than keeping track of a set of numpy arrays and just stacking them. The stack operation is incredibly computationally prohibitive. So for something like this that's already computationally expensive, doesn't make any sense. And keep track of the total number of memories stored, so that way you don't overwrite the array. We want to keep track of how often we want to replace the target network. And then we need our two networks QEval. And that is just, pass in the alpha, that is just the agent's estimate of the current set of states. And Q next is the agent's estimate of the successor set of states. So recall in deep Qlearning, we calculate the value, the max value of the successor state as our greedy action. That's our actual target policy, and our behavior policy that we use to generate data is epsilon greedy. That's it for our constructor. The next thing we have to worry about is storing memory transitions. So transmission. So we are interested in the current state, the action taken, the reward received, and the resulting state, because those are the things that allow the agent to learn. So we have to make sure that we aren't over our memory. So if the mem counter is less than self.mem size, then just go ahead and append that as a list. And again, we're doing this because it is much cheaper computationally to append a list than it is to actually stack a numpy array. If we have filled up our memory, then we want to overwrite the position in memory that is determined by the modulus .mem size. So this will guarantee we're bounded by 0 all the way up to our mem size. And of course, this is a list of lists. It's just state action reward state underscore. And we want to increment the memory counter. Pretty simple, huh? Pretty straightforward. Next up, we have the function to choose an action. And this will take the observation. And again, just to remind you, as we discussed in the first video, we're passing in a sequence of observations because we want to capture some information about the temporal dependence of what's going on. Again, with one frame, you can't tell if the aliens are moving left or right, and so you don't know if you should move left or right. Of course, you know which way your bullets go, you know which way theirs go, but as far as movement's concerned, you need at least one frame. So, as always, we're going to be using numpy to calculate a random number for our epsilon greedy action selection. And you want to get the value of all of the actions for the current set of states. Self qeval.forward. So what we're doing now is forward propagating that stack of frames through the neural network, the convolutional neural network, and the fully connected layer to get the value of each of the actions given that you're in some set of states denoted by the observation. So if rand is less than 1 minus epsilon, then you want to take the argmax, right, the maximum action. And recall that we have stored the actions as a matrix. They're returned as a matrix because you have the number of rows that correspond to the number of frames you pass in, and each of the columns correspond to each of the 6 actions. So you want to take the first axis. And if you're taking a random action, then you just choose something at random from the action space list. And go ahead and increment your steps and return the action that you've chosen. The reason I use 1 minus epsilon is you can use the probability epsilon. You can use probability 1 minus epsilon. This is really more of a soft epsilon kind of strategy rather than purely greedy, but it doesn't really matter. This is going to give you the probability of choosing the maximum action of epsilon plus epsilon over 6 because of course, the greedy action is the subset of all actions. So there's a 1 over 6 probability that when you take the quote unquote non-greedy action, you'll actually end up getting the greedy action. All right. Next thing we have to worry about is how the agent is going to learn. And this is really the meat of everything. So we are doing batch learning. So you want to pass in a batch size. And the reason we're doing batch learning is a number of different reasons. So you want to break correlations between state transitions. It's even okay if the batch overlaps different episodes. What you want to get is a good subsampling of the overall parameter space, so that way you don't get trapped in a local minima. So you randomly sample these state transitions through your memory. Otherwise, you could end up, if you replay the whole memory, you could end up getting trapped in some local minima. It's a way to improve the efficiency of the algorithm to converge to a purely optimal strategy. Excuse me. On Thursday. All right. First thing we have to do, since we're using batch learning, is we have to zero out our gradients. And what this means is that the gradients can accumulate from step to step. The network, the PyTorch library can keep track of it. We don't want that. If you do that, if you don't do the zero grad, then you'll end up with basically accumulating for every single batch. And that's really full learning rather than batch learning. Next thing we have to check for is if we're going to replace the target network. So if it's not none, and if it's time to do it, replace target count equals 0, then we want to actually replace our target network. What we do there is we take advantage of the PyTorch representation of our network. In that case, it's just we can convert our entire network into a dictionary, which is really cool. So it's self qnext.load state dict. So it's going to load a state to the network from a dictionary. Which network? The evaluation network, which we're going to convert to a state dictionary. We're not actually going to use this in our implementation, but I included it here for completeness. Next up, we want to know, we want to select a random subsample of the memory. So we want to make sure we don't go all the way past the end of our array. So if our current memory counter plus batch size is less than our total memory, then we're free to go ahead and select any point of our memory, because we know we're not going to go beyond it. Range. Otherwise, if there is an overlap, then we want memstart to just be an int in the range. Good grief. I hate that. -1, just to be safe. Okay, so that is how we choose where to start, just a random number somewhere between 0 and the max memory if we have enough left over in the memory for the batch to accommodate the batch. Otherwise, subtract that off and select something from that subset. Then we're going to go ahead and get that mini batch. And convert that to a numpy array. So I suspect this is not the most efficient way of doing this. And the reason is that you run into some difficulties in the way in which you pass things into the Torch library. It has a certain set of expectations that are kind of finicky. Not to say it's bad, it's just something that I wasn't expecting, but it works nonetheless. So what we want to do next is feed forward both of our networks. We want to know what is the value of our current state and what is the value of the successor state after we take the action, whatever action we're looking at in our batch. So that's just qeval forward. What are we feeding forward? Here's where we got some hackiness. We got to convert it into a list. And the reason is that our memory is a numpy array of numpy objects because the observation vectors are numpy objects. So if you don't convert it into a list, then you have a numpy array of ND array objects, and PyTorch will complain. We don't want PyTorch to complain. So we want to access all rows, right? Our entire batch, and the state is just the 0th element. And you want all of the variable, you want all of the pixels. So you need the second set of colons there, and we want to send this to the device. self.qeval.device. And this ensures that this network, this set of variables gets sent to our GPU as well. And the next thing we need is the value of the successor states. And that is just all the rows, third column, and all of the members of that array. And here I've just I gotta quit using the Visual Studio Code. This is annoying, but scroll up here. So all I have done here is I'm putting it on qeval.device because the device for both the evaluation and the next network are the same. So I only have one GPU. If I had two GPUs, then this would matter. It doesn't matter. So you can just call it that. Next thing we want to know is what is the max action for our next state, right? Because the update rule actually takes into account the purely greedy action for the successor state. Maybe if I can find an image of it, I'll flash it here on the screen to make life easy. But next thing we have to know is the max action, and we use the argmax function for that. And remember, we want to take the first dimension because we're the actions qnext, qpredicted, and qnext are actually our actions. That's what we get from the feed forward, and that is batch size times number of actions, and we want the number of actions. So that's the first dimension. And I am a little bit inattentive here about sending it to the device just to make sure nothing gets off the device, because this stuff slows to a crawl if you run it on the CPU. We need to get our rewards, and that is obtained from our memory, all the rows, and the second element. Too many parentheses. And one thing we want is our loss function to be 0 for every action except for that max action. So we have qtarget equal qpredicted, but we want qtarget for all of our entire batch, but the max action to be rewards plus self.gamma times the actual value of that action. So t.max just gives you the value of the maximum element, and argmax gives you the index. And you want to find the maximum action, the value of it. So those are our target and predicted values. That's what we use to update our loss function. The next thing we have to handle is the epsilon decrement. So we want the agent to gradually converge on a purely greedy strategy for its behavior policy. And the way you do that is by gradually decreasing epsilon over time. I don't like to let it simply go to start decreasing right away. So I have some set number of steps. I let it run first. And I use a linear decrease over time. You can use exponential, quadratic. You can use whatever form you want. It's not, to my knowledge, it's not super critical, but I could be completely wrong. This seems to work, as we'll see in the third video. So if we don't have enough left, then just set it to epsilon end. Scroll up here, and we're almost done. So we have everything we need. We have everything we need to compute our loss, which is this qtarget and qpredicted. Those are the values of qpredicted is the value of the current set of states, and qtarget is related to qnext, right? It's the qtarget is the max action for the next successor state. And so we're almost there. So the loss is just the mean squared error loss. If you recall from the first video where we defined the loss function, and as is the torch style, you have to send it to the device. And then we want to back propagate with loss backward, and we just want to step. Perform one iteration and go ahead and increment our learn step counter. And that's basically it. So there was a lot of code there. Let's go back and take a look really quick. So first thing you want to do is zero your gradients. So that way we're doing actual batch optimization instead of full optimization. Then we want to check to see if we're going to, if we are going to replace the target network, and if it is time, and if it is, load the state dictionary from the QEval onto the QNext network. Next up, calculate the start of the memory subsampling, making sure to get some subset of the array. Go ahead and sample that batch of memory and convert it to a numpy array. Oh, Pomodoro timer. So if you guys aren't using the Pomodoro method to work, I highly recommend it. Go look that up if you don't know what it is. But anyway, convert that to a numpy array, and then go ahead and feed forward the current state and the successor state using the memory subsample, making sure to set it to your device. Next thing we have to know is the maximum action for the successor state, and calculate the rewards that the agent was given. Set the Q target to Q predicted because we want the loss for every state except the loss for every action except the max action to be 0. And then update the value of Q target for the max action to be equal to rewards plus gamma times the actual value of that max action. Next up, make sure that you're using some way of decrementing epsilon over time such that it converges to some small value that makes the agent settle on a mostly greedy strategy in this case. I'm using 5% of the time for a random action. Finally, go ahead and calculate the loss function, backpropagate it, step your optimizer, and increment your step counter. And that is all she wrote for the learn function and the agent class. Slightly more code than in the network class, but still fairly, we have a typo there, still fairly straightforward. I hope this has been informative. And in part 3, we're going to go ahead and code up the main loop and see how all this performs. I look forward to seeing you in the next video. Any comments, questions, suggestions, go ahead and leave them below. If you made it this far, please consider subscribing. I look forward to seeing you all in the next video. And welcome back, everybody, to part 3 of coding a deep Qlearning agent in the OpenAI Gym Atari library. In parts 1 and 2, we took a look at the deep neural network class as well as the agent class for our agent. And in part 3, we're going to finally put it all together into the main loop to play the game and see how our agent does. Let's get started. So we begin as usual with our typical imports. We're going to need the gym, of course, and we're going to need to import our model class. So from model, we're going to import deep Q model and agent. And I also have a utility function. I'm not going to go over the code. It's just a trivial function to post the to plot the decaying epsilon and the running average of the previous 5 scores. From utils, import plot learning, and and by the way, so if you haven't seen parts 1 and 2, go ahead and check those out. If you want the code for this, please check out my GitHub. If you would like to see a blog article that details all this in text, if you missed something in the speech, then go ahead and click the link down below. So it's giving me some issue. It's not DBQ model. This is the downside of talking and typing at the same time. I'm not that talented. So we want to go ahead and make our environment. And that's Space Invaders V0. Another thing to know is that there are implementations of the environment where instead of being passed back an image of the screen, you're passed back like a RAM image, something like that. I've never used it. Sounds kind of interesting. It might be something for you to check out, and leave a comment down below if you've played with, have any experience with it, or if you think it sounds cool. So we want to make our agent, and I'm going to call it Brain. Big Brain. Pinky in the brain, baby. Gamma 0.95, and epsilon of 1.0, and I'm using epsilon of 1.0 because it starts out taking purely random actions and converges on a mostly greedy strategy. Learning rate is 0.03, max memory size, 5,000 transitions, and we're not going to do any replacement. So you may have noticed when we were building our agent that the memory was instantiated as an empty list. If you're going to use numpy arrays, one thing you would do is just create an array of zeros in the shape of your images, as well as the total number of memories. I'm going to do something slightly different. So one way to help agents learn is to actually have them watch videos of humans playing. And in fact, the DeepMind team taught AlphaZero Go to play it by showing it board configurations and saying which player won. So it's perfectly legitimate to leverage the experience of humans. I'm not going to play the game for the agent, but what I'm going to do is allow the agent to play the game at totally random. It's just going to play a set number of games to fill up its memory using totally random actions. So it's a bit of a hack, but I don't know. To me, it seems legitimate, but some people may frown upon it. I don't really care. It's how I chose to solve the problem, and it seems to work fairly well. So brain.mem size, we have to reset your environment, reset your done flag, and play an episode. So here I'm going to let you know the actions. So 0 is no action, 1 is fire, 2 is move right, 3 is move left, 4 is move right, fire, 5 is move left, fire. So that's 0 through 5, total of 6 actions. Choose one at random. env.action space.sample. If you want to verify that these do that, go ahead and code up a simple loop, a while loop while not done. Take action 0 and render it and see what it does. So next you want to go ahead and take that action. And the other thing I do is and I'm on the fence about doing this. I haven't tested it, but in my experience with other environments in more basic algorithms, that my experience is that it makes sense to penalize the agent for losing. So the agent will naturally try to maximize its score, but you want it to know that losing is really bad. So if you're done and this may be something I change on the GitHub. So if you go to the GitHub and see this isn't there, it means that I tested it and decided it was stupid. But as of right now, I think it's okay. I'm always open to change my mind, though. So I want to let it know that losing really, really sucks. And I want to store that transition. And here's a bit of a magical part. So as I said in the first video, in the convolutional neural network, we want to reshape it down from 3 channels into 1 because the agent doesn't really care about color. It only cares about is an enemy there or not, right? And it can get that information from black and white. So I'm going to take the mean over the 3 channels to get down to a single channel. And I'm also going to go ahead and truncate it. And the reason is that there isn't a whole lot of information around the borders of the screen that the agent needs. So we can get away with reducing our memory requirements without losing anything meaningful. And I'm going to go ahead and flash in some images here of what that looks like. But what I'm going to do is take the observation vector, and I'm going to take 15 to 200 and 30 to 125. And the mean is performed over axis 2. And we also want to store our action and reward. You guys can't see that there. So we store the action and reward, as well as, let's go ahead and copy this. We also want to store the successor state. Oh, good grief. Life is so hard. There we go. And that's observation underscore, which is the successor state. And then set your observation to observation underscore. And then when you're done, just let yourself know. Okay. And we are almost there. So next thing you want to do is keep track of the scores. You want to know how well the agent is doing. I had this variable epsilon history. Keep track of the history of epsilons as it decreases over time, because we want to know the relationship between the score and the epsilon. And we'll run it for 50 games, and we'll take a batch size of 32 memories.
The batch size is an important hyperparameter, but what you find is that using a large batch size may get you a little bit better performance. It slows down training tremendously. So on my system with an i7 7820X, 32 gigs of RAM, 1080 Ti, batch size of 32 means that 50 games is going to run in about half an hour. That takes quite a bit of time. Using a larger batch size doesn't seem to produce a whole lot better performance, but it certainly slows it down by more than a factor of 2. So there's nonlinear scaling there. And we want to know that we're starting game I plus 1 with an epsilon of something. Say 4 significant figures. Right out epsilon. And we want to go ahead and append the agent's epsilon at the beginning of the episode, reset our done flag, and reset our environment. And okay, so the next thing we want to do is, as I said, why is this unhappy? Invalid syntax. Oh no, I've offended it. What have I done? Oh, forgot a comma. There we go. So next thing we want to do is construct our sequence of frames. As I said, we're going to pass in some sequence of frames to allow it to get some conception of movement in the system. So I have a rather ugly way of doing this, as usual. But the first thing I'm going to pass into it is the first observation vector from the beginning of the game. And I have broken something again. What have I broken? Frames, numpy, sum. Oh. Of course. Of course. Okay. So the score for this episode is 0. I want to keep track of the last action. So this is something I'm not sure about, I must confess to you guys. The documentation on the OpenAI Gym is rather lackluster. What it says is that each action will be repeated for k frames, where k is the set 2, 3, or 4. So I guess it gets repeated some random number of times. So since I don't know how many times and I want to keep passing in a consistent set of observation vectors of frames, I will do something hacky. So I'll keep track of the last action, and I will only update my action every third action. So I want to pass in a sequence of 3 frames and repeat the action 3 times. I'm kind of forcing the issue. Again, it seems to work. I don't think it's the best implementation, but this is, just my quick and dirty implementation. So if we have 3 frames, go ahead and choose an action based on those and reset your frame variable to an empty list. Otherwise, go ahead and do what you just did. Scroll down. So then we want to go ahead and take that action. Keep track of our score and append our new observation. I'm just going to copy that. Yeah. Copy that. And then I am going to go ahead and tell it that losing is very bad. We don't like losers. And this al.lives thing is the number of lives the agent has. AL is just the emulator on which the OpenAI Gym's Atari library is built. And next we have to store a transition. I'm going to copy that code precisely because I have fat fingers and apparently screw things up. So copy that. And then underscore brain.learn batch size. Keep track of our action. And here you can put in a render if you want to see what it's doing. If not, then at the end of the episode, you're going to append a score, which we're going to plot later. And I like to print the score so that I can kind of get an idea of how the agent's doing. And we need to make a list of the X variable for our plotting function. Again, for the plotting function, just go ahead and check out my GitHub for that. That's the easiest way. And I'm going to set a file name. I'm just going to call it test for now, plus string numgames, something like that. Plus .png. So we have a file name. And then we're going to plot that. We want to plot the scores, the Epsilon history, and the file, and pass in the file name so that it saves it. And that's all she wrote for the main loop. I've gone ahead and run that, so I'm going to go ahead and flash in the results here. So as you can see, the Epsilon decreases somewhat linearly over time, not somewhat, completely linearly. And as it does so, the agent's performance gradually increases over time. And keep in mind here, I am plotting the average of the previous 5 games. The reason I do that is to account for significant variations in game-to-game play, right? So the agent is always going to choose some proportion of random actions, and that means it can randomly choose to move left or right into the enemy's bullet. So there's always some games that's going to get cut short. So the general trend in the performance is up until the very end when it actually takes a bit of a dive. And I've seen this over many, many different iterations. I suspect this has to do with the way that it is navigating through parameter space. It'll find pretty good pockets and then kind of shift into a related other local minima, what isn't quite as good. If you let it run long enough, this will eventually go back up. But it does have some oscillatory behavior to it. But you can see that it increases its score quite dramatically. And in this particular set of runs, I saw scores in excess of 700 points, which is actually pretty good for an agent. So let's go ahead and take a look at what it looks like with the target network replacement. So here you can see a dramatically different behavior. So in this case, Epsilon decreases and the score actually decreases over time. And, actually, I don't quite know why it does this. So the oscillations down there are almost certainly from the target network replacements. It could be a fluke, but I have run this several times where I see this type of behavior where with the target network replacement, it totally takes a nosedive. I don't think I screwed up my implementation. Please leave a comment below if you saw something that looks off, but as far as I can tell, it's implemented correctly. You just copy one state dict to another. No real big mystery there. But that's why I choose to leave it off. You get a significant variation in performance. Moral of the story is to go ahead and leave the target network replacement off. And that's it for this series. So we have made an agent to play the Atari game of Space Invaders. By gradually decreasing Epsilon over time, we get really good performance, several hundred points. In fact, actually learns how to play the game quite well. I'm probably going to go ahead and spin in a video of it playing here so you can see how it looks. If this has been helpful to you, please consider subscribing. Go ahead and leave a comment below if you have one, a question, suggestion, anything. Go ahead and I answer and read all my comments. Go ahead and smash that like button, guys. So I hope to see you all in the next video, and take care.
In this video, I'm going to tell you everything you need to know to start solving reinforcement learning problems with policy gradient methods. I'm going to give you the algorithm and the implementation details up front, and then we'll go into how it all works and why you would want to do it. Let's get to it. So here's a basic idea behind policy gradient methods. A policy is just a probability distribution the agent uses to pick actions. So we use a deep neural network to approximate the agent's policy. The network takes observations of the environment as input and outputs actions selected according to a softmax activation function. Next, generate an episode and keep track of the states, actions, and rewards in the agent's memory. At the end of each episode, go back through these states, actions, and rewards and compute the discounted future returns at each time step. Use those returns as weights and the actions the agent took as labels to perform backpropagation and update the weights of your deep neural network. Then just repeat until you have a kick-ass agent. Simple, yeah? So now we know the what. Let's unpack how all this works and why it's something worth doing. Remember, with reinforcement learning, we're trying to maximize the agent's performance over time. Let's say the agent's performance is characterized by some function, j, and it's a function of the weights, theta, of the deep neural network. So our update rule for theta is that the new theta equals the old theta plus some learning rate times the gradient of that performance metric. Note that we want to increase performance over time, so this is technically gradient ascent instead of gradient descent. The gradient of this performance metric is going to be proportional to sum over states for the amount of time we spend in any given state, and a sum over actions for the value of the state-action pairs and the gradient of the policy, where of course the policy is just the probability of taking each action given we're in some state. This is really an expectation value, and after a little manipulation, we arrive at the following expression. When you plug that into the update rule for theta, you get this other expression. There are two important features here. This g sub t term is the discounted future returns we referenced in the opening, and this gradient of the policy divided by the policy is a vector that tells us the direction in policy space that maximizes the chance that we repeat the action a sub t. When you multiply the two, you get a vector that increases the probability of taking actions with high expected future returns. This is precisely how the agent learns over time and what makes policy gradient methods so powerful. This is called the reinforce algorithm, by the way. If we think about this long enough, some problems start to appear. For one, it doesn't seem very sample efficient. At the top of each episode, we reset the agent's memory so it effectively discards all its previous experience. Aside from the new weights that parameterize its policy, it's kind of starting from scratch after every time it learns. Worse yet, if the agent has some big probability of selecting any action in any given state, how can we control the variation between the episodes? For large state spaces, aren't there way too many combinations to consider? Well, that's actually a non-trivial problem with policy gradient methods, and part of the reason our agent wasn't so great at Space Invaders. Obviously, no reinforcement learning method is going to be perfect, and we'll get to the solution to both of these problems here in a minute. But first, let's talk about why we would want to use policy gradients at all, given these shortcomings. The policy gradient method is a pretty different approach to reinforcement learning. Many reinforcement learning algorithms, like deep Qlearning for instance, rely on estimating the value of a state or state-action pair. In other words, the agent wants to know how valuable each state is so that its epsilon greedy policy can let it select the action that leads to the most valuable states. The agent repeats this process over and over, occasionally choosing random actions to see if it's missing something. The intuition behind epsilon greedy action selection is really straightforward. Figure out what the best action is and take it. Sometimes do other stuff to make sure you're not wildly wrong. Okay, that makes sense, but this assumes that you can accurately learn the action value function to begin with. In many cases, the value or action value function is incredibly complex and really difficult to learn on realistic timescales. In some cases, the optimal policy itself may be much simpler and therefore easier to approximate. This means the policy gradient agent can learn to beat certain environments much more quickly than if it relied on an algorithm like deep Qlearning. Another thing that makes policy gradient methods attractive is, what if the optimal policy is actually deterministic? In really simple environments with an obvious deterministic policy, like our grid world example, keeping a finite epsilon means that you keep on exploring even after you found the best possible solution. Obviously, this is suboptimal. For more complex environments, the optimal policy may very well be deterministic, but perhaps it's not so obvious and you can't guess at it beforehand. In that case, one could argue that deep Qlearning would be great because you can always decrease the exploration factor Epsilon over time and allow the agent to settle on a purely greedy strategy. This is certainly true, but how can we know how quickly to decrease Epsilon? The beauty of policy gradients is that even though they are stochastic, they can approach a deterministic policy over time. Actions that are optimal will be selected more frequently, and this will create a sort of momentum that drives the agent towards that optimal deterministic policy. This really isn't feasible in action value algorithms that rely on epsilon greedy or its variations. So what about its shortcomings? As we said earlier, there are really big variations between episodes, since each time the agent visits a state, it can choose a different action, which leads to radically different future returns. The agent also doesn't make very good use of its prior experience, since it discards them after each time it learns. While they seem like showstoppers, they have some pretty straightforward solutions. To deal with the variance between episodes, we want to scale our rewards by some baseline. The simplest baseline to use is the average reward from the episode, and we can further normalize the g-factor by dividing by the standard deviation of those rewards. This helps control the variance in the returns so that we don't end up with wildly different step sizes when we perform our update to the weights of the deep neural network. Dealing with the sample inefficiency is even easier. While it's possible to update the weights of the neural net after each episode, nothing says this has to be the case. We can let the agent play a batch of games so that it has a chance to visit a state more than once before we update the weights for our network. This introduces an additional hyperparameter, which is the batch size for our updates, but the trade-off is that we end up with a much faster convergence to a good policy. Now, it may seem obvious, but increasing the batch size is what allowed me to go from no learning at all in Space Invaders with policy gradients to something that actually learns how to improve its gameplay. So that's policy gradient learning in a nutshell. We're using a deep neural network to approximate the agent's policy, and then using gradient ascent to choose actions that result in larger returns. It may be sample inefficient and have issues with scaling the returns, but we can deal with these problems to make policy gradients competitive with other reinforcement learning algorithms like deep Qlearning. If you've made it this far, check out the video where I implement policy gradients in Tensorflow. If you like the video, make sure to like the video, subscribe, comment down below, and I'll see you in the next video.
What's up, everybody? In this tutorial, you're going to learn how to land a spaceship on the moon using policy gradient methods. You don't need to know anything about reinforcement learning. You don't need to know anything about policy gradient methods. You just have to follow along. Let's get started. So before we begin, let's take a look at the basic idea of what we want to accomplish. Policy gradient methods work by approximating the policy of the agent. The policy is just the probability distribution that the agent uses to select actions. So we're going to use a deep neural network to approximate that probability distribution, and we're going to be feeding in the input observations from the environment and getting out a probability distribution as an output. The agent learns by replaying its memory of the rewards it received during the episode and calculating the discounted future rewards that followed each particular time step. Those discounted future rewards act as weights in the update of our deep neural network so that the agent assigns a higher probability to actions whose future rewards are higher. So we'll start with our imports, and we're going to want OS to handle file operations, numpy to handle numpy type operations, and of course Tensorflow to develop our agent. We're going to stick everything in one class, whose initialize function takes the learning rate, the discount factor gamma, the number of actions for the lunar lander environment, that's just 4, the size of the first hidden layer of the neural network, we'll default that to 64. The size of the second hidden layer of the deep neural network will also default that to 64. We also need the input dims, and in this case that is 8. So the observation isn't a pixel image, it is just a vector that represents the state of the environment. We also want a checkpoint directory, and this will be useful for saving our model later. So this action space will be what we use to select actions later on. And we're going to need a number of other administrative type stuff. So for instance, the state memory is just what the agent will use to keep track of the states it visited. Likewise, for the action memory, we want to keep track of the actions the agent took and the rewards it received along the way. We also need the layer 1 size and the layer 2 size. What else? Okay, so now we can move on to the administrative stuff with Tensorflow. So Tensorflow handles everything in what are called sessions. So we have to define one of those. We're going to need a function to build the network. And when we return from the network, we're going to want to initialize all of the variables. So this build network function is only called once. It will load up all of the variables and operations under the Tensorflow graph. And then we have to initialize those variables with some initial values, which will be done at random. We also need a way of saving the model because your PC may not be fast enough to run this in a short enough amount of time. So you can do this in chunks by saving it and then reloading it as you have time. We also need a file to save the checkpoints in. So our next order of business is to actually construct this network. So we don't need any inputs for that, but we do need a set of placeholders, and the placeholders serve as placeholders for our inputs. It just tells the TensorFlow graph that, hey, we're going to be passing in some variables. We don't know what they are yet. We may not necessarily even know their shape or size, but we know what type they are, and we want to give them names so if something goes wrong, we can debug later. So this input will just be the 8-element vector that represents the agent's observation of the environment. And if you're not really familiar with TensorFlow, this idiom of saying shape equals a list whose first element is none tells TensorFlow that we do not know the batch size of the data we're going to be loading. So the inputs could be 10 states, it could be 100, it could be 1,000, it could be any number of states. And so that none just tells TensorFlow, hey, we don't know what shape it's going to be, so just take whatever. And this label is going to be the actions the agent took during the course of the episode. This will be used in calculating our loss function. Similarly, we have something called G. And G is just the generic name for the agent's discounted future rewards following each time step. This is what we will use to bias the agent's loss function towards increasing the probability of actions who generate the most returns over time. So now we're going to construct our network. So the first layer will just be the input, and the number of it'll take, of course, number of input and input dims on input, and then output the layer 1 size, and the activation is just going to be a ReLU function. And then we have to worry about initializing this. So when we call the tf.globalVariables initializer, it's going to initialize all of the layers and variables with some values. We can dictate how it does that, and we can think very carefully about it. So if you've dealt with deep neural networks, in some cases you can get vanishing or exploding gradients that cause the values that the network predicts to, go to, either really large or really small values. It produces junk, essentially. There is a function that will initialize the values of all the layers such that they are relatively comparable and we have a minimal risk of that happening. And that's called the Xavier initializer. And I'm going to want to copy that because we're going to use that more than once. So of course the second layer just takes the first layer's input, has L2 size as the number of units with a ReLU activation. And of course the same initializer. And L3 will be the output of our network. However, we don't want to activate it just yet. So this quantity is related to the the policy of the agent, but the policy must have the property that the sum of the probabilities of taking an action, the sum of the probabilities for all of the actions must equal 1. And it's the softmax function that has that property. And we're going to separate it out so that we can so that it is a little bit more clean in terms of the code, a little bit more readable for us. But the self.actions variable is what will actually calculate the probabilities of selecting some action. And that is just the softmax of the L3, and the name of that is probabilities. Finally, we need to, well, not finally, but next we need to calculate the loss function. So you'll stick that in a separate scope. And what we need is the negative log probability. So, the calculation involves the natural log of the policy, and you want to take the gradient of the natural log of something. So we need a function that matches that property. So we'll call it neg log probability, and that's the sparse softmax cross entropy with logits. Try saying that 5 times fast. So logits is just L3. And this is important because this is part of the reason we separated out L3 and actions, because when you're passing in the logits, you don't want it to already be activated, because the sparse softmax cross entropy will handle the softmax activation function. And the labels will just be the label that we pass in from the placeholder, and then of course be the actions the agent took. And so the loss is then that quantity, neg log probability, multiplied by the returns, G. Next we need the training operation. And that, of course, is just our gradient descent type algorithm. In this case, we'll use the atom optimizer. The learning rate of whatever we dictate in the constructor, and we want to minimize that loss. So that is the sum and whole of the deep neural network we need to code. The next question we have is, how can we select actions for the agent? So the agent is attempting to model its own probability distribution for selecting actions. So that means what we want to do is take a state as input, pass it through the network, and get out that probability distribution at the end given by the variable self.actions. And then we can use numpy to select a random action according to that probability distribution. And we're just going to go ahead and reshape this. Abilities. So when you run an operation through the TensorFlow graph, you need to specify a feed dictionary, which gives the graph all of the input placeholder variables it's expecting. So in this case, it wants self.input, and that takes state as input, and it's going to return a tuple. So we're going to take the 0th element as, so we can get the correct value that we want. And then we can select an action according to numpy random choice from the action space using the probabilities as our distribution. And we just return that action. The next problem we have to deal with is storing an action. The transitions. And of course we'll store the state, action, and reward. And this will be useful when we learn. And since we're using lists here, we're just going to append the elements to the end of the list. Next, we come to the meat of the problem, the learning function. And this doesn't require any input. So the basic idea here is that we are going to convert these lists into numpy arrays so we can more easily manipulate them. And then we're going to iterate through the agent's memory of the rewards it received and calculate the discounted sum of rewards that followed each time step. So we're going to need 2 for loops and a variable to keep track of the sum, as well as something to keep track of our discounting. So let's deal with the memories first. That won't work, will it? There we go. So now we'll instantiate our G factor and get in shape of reward memory. We will iterate over the length of that memory, which is just the length of our episode. And so for each time step, we want to calculate the sum of the rewards that follow that time step. Is that correct? Yes. Next, we take the sum and discount it. Then, of course, the discount is just the gamma to the k, where k is our time step. So then, of course, the rewards following the the t time step is just g sum. So that's the sum. That's the weighted discounted rewards. The next thing we have to think about is these rewards can vary a lot between episodes. So to promote stability in our algorithm, we want to scale these results by some number. It turns out that a reasonable number to use is the mean. So we're going to subtract off the mean of the rewards the agent received during the episode and then divide by the standard deviation. And this will give us some nice scaled and normalized numbers such that the algorithm doesn't produce wonky results. And since we're dividing by the standard deviation, we have to account for the possibility that the standard deviation could be 0. Hence the conditional statement. Next, we have to run our training operation. So the underscore tells us we don't really care about what it returns, but we have to run the training operation with the feed dictionary. That'll take an input, which is just our state memory. It will take the labels, and that is just the action memory. And it will take the G factor, which is just the G we just calculated. Now at the end of the episode, once we finish learning, we want to reset the agent's memory so that rewards from one episode don't spill over into another. So there are two more functions we need. These are administrative. We need a way to load the checkpoint. And we'll go ahead and print out loading checkpoint just so we know it's doing something. And then we have the saver object, and we want to restore a session from our checkpoint file. Next, we want to save a checkpoint. We're not going to print here, I take it back. The reason is that we're going to be saving a lot, and I don't want it to print out a bunch of junk statements. So and what these are doing is just either taking the current graph as it is right now and sticking it into a file, or conversely taking the graph out of the file and loading it into the graph for the current session. So that is that. Next, we can move on to the main program to actually test our lander. So we'll need Jim, and I don't know if I made it clear at the beginning, but you'll also need the box2d-pi environment. So go ahead and do pip install box2d-pi if you don't already have that. So we'll need to import our policy gradient agent. I have this plot learning function I always use. You can find it on my GitHub along with this code, of course. I don't elaborate on it, but basically what it does is it takes a sequence of rewards, keeps track of it, performs a running average of, say, the last 20, 25, whatever amount you want, and spits that out to a file. We also have a way of saving the renderings of the environment. So it runs much faster if you don't actually render to the screen while it's training, but you can save those renderings to files in MP4 files so you can go back and watch them later. It's how I produce the episodes you saw at the beginning of this video. So first thing we want to do is instantiate our agent. And we'll use a learning rate of 0, 3 zeros, and a 5. And I believe, we'll need a gamma. We'll use something like 0.99. And then all the other parameters we'll just leave at the defaults. Next, we need to make our environment. And that's Lunar Lander v2. A way to keep track of the scores the agent received, our initial score, and number of episodes. So I achieved pretty good results after 2,500 episodes, so we can start with that. So the first thing we want to do is iterate over our episodes. Oh, let me do this for you. So before we do that, I'll comment this out, but if you want to save the output, you do this. env equals wrappers.monitor, pass in the environment wherever you want to save it, Lunar Lander, and then you want to use a lambda function to tell it to render on every episode. And this force equals true. I believe that just tells it to overwrite if there's already data in the directory. So at the top of every episode, just print out what episode number you're on and the current score. You set your done flag, and for subsequent episodes you'll want to reset the score, reset your environment, and play an episode. First thing you want to do is select an action. and that takes the observation as input. So we need to get the new observation, reward, done flag, and info by stepping through the environment. Once that's done, you want to store the transition. Set the old observation to be the new one so that you select an action based on the newest state. And keep track of the reward you received. At the end of every episode, we want to append the score to the score history and perform our learning operation. You also want to save a checkpoint after every operation, after every learning operation. And then when you're done, dictate some file name, .png, and call my super secret plot learning function. That just takes the score history, file name, and a window that tells it over how many games you want to take the running average. So now let's go to our terminal and see how many mistakes I made. 1 second. All right, so here we are. Let's go ahead and give it a try. So I made some kind of error in the policy gradient agent. Let's swing back to that file and see where it is. 1 second. So here's the model. It does not have input dims. That's because I forgot to keep track of it. Save. Go back to our terminal and see how it does. And I apparently called something I should not have. This is line 27. It says self.label placeholder got an unexpected keyword argument named label. Ah, that's because it is called name. That's what happens when I try to type and talk at the same time. So let me make sure I didn't call L1 size, L2 size something different. No, I did not. All right, I will run that again. So now it's unhappy about the choice of, oh, of course. So it's lunar, there's no dash in there. Get rid of that. Typos galore tonight. Oh, really? Oh, really? Ah, it's store transitions. Yes. So it's actually store transitions, so let's call it that. And there we go. Perfect. So now it's actually learning. I'm not going to sit here and wait for this to do 2,500 games because I've already run this once before. That's how I got the code you saw at the beginning. So I'm going to go ahead and show you the plot that it produces now so you can see how it actually learns. So by the end, it gets up to about an average reward of around 200 and above points. That's considered solved if you check the documentation on the OpenAI Gym. So congratulations, we have solved the lunar lander environment with a policy gradient algorithm. Relatively simple, just a deep neural network that calculates the probability of the agent picking an action. So I hope this has been helpful. Go ahead and leave a comment down below. Feel free to take this code from my GitHub, fork it, make it better, do whatever you want with it. I look forward to seeing you all in the next video. Welcome back, everybody, to a new reinforcement learning tutorial. In today's episode, we're going to teach an agent to play Space Invaders using the policy gradient method. Let's get to it. For our imports, we start with the usual suspects, numpy and Tensorflow. We start by initializing our class for the policy gradient agent. We take the learning rate, discount factor, number of actions, number of layers for the fully connected layer, the input shape, channels, a directory for our checkpoints, very important, as well as a parameter to dictate which GPU we want Tensorflow to use. If you only have one GPU or using the CPU, you don't need that parameter. Save the relevant parameters and compute the action space, which is just a set of integers. We want to subtract out the input heights and width from the input shapes and keep track of the number of channels for use later. Our agent's memory will be comprised of 3 lists that keep track of the state, action, and rewards. We want a configuration which just tells TensorFlow which GPU we want to use, as well as our session graph that uses that config. We call the build network function and then use the TF global variables initializer. We need to keep track of a saver and a checkpoint file for saving and loading the model later. Now, if you don't know anything about policy gradient methods, don't worry, we're going to cover everything you need to know as we go along. The first thing we're going to need is a convolutional neural network to handle image preprocessing. That'll be connected to a fully connected layer that allows the agent to estimate what action it wants to take. In contrast to things like deep Qlearning, policy gradient methods don't actually try to learn the action value or value functions. Rather, policy gradients try to approximate the actual policy of the agent. Let's take a look at that. For our build network function, we're going to construct a convolutional neural network with a few parameters. An input placeholder that has shape, batch size by input height and width, as well as the number of channels. We will also need an input for the labels, which just correspond to the actions the agent takes. That has shape batch size. And a factor G, which is just the discounted future rewards following a given time step. That has shape batch size. Our convolutional neural network is going to be pretty straightforward. If you've seen any of my videos, you can kind of know what to expect. The first layer has 32 filters, a kernel size of 8 by 8, and a stride of 4. And we're going to want to use an initializer for this. I found that the Xavier initializer works quite well. The purpose of it is to initialize all the parameters in such a way that the network doesn't have one layer with parameters significantly larger than any other. We want to do batch normalization. I mistyped the epsilon there. It should be 1 by 10 to the minus 5. And you want to, of course, use a ReLU activation on the first convolutional layer. And that that activated output serves as the input to the next layer with 64 filters, kernel size of 4 by 4, and a stride of 2. And again, we'll use the Xavier initializer. Of course, we also want to do batch normalization on this layer, and at this point I think I actually get the correct epsilon for the batch norm. And of course we want to use a ReLU activation on that batch normed output as well. Our third convolutional layer is more of the same, 2D convolution with 128 filters. It will have a kernel size of 2 by 2, a stride of 1, and we'll also use the same initialization. Again, batch normalization with an epsilon of 1 by 10 to the minus 5. Activate with a ReLU. Next, we have to take into account our fully connected layers. So the first thing we need to do is flatten the output of the convolutions. Because they come out as matrices, we need a list. Go ahead and make the first fully connected layer using FC1 as the number of units, ReLU activation. And the second dense layer is going to have units equal to the number of actions for the agent, which in this case is just 6. Notice that we don't activate that, but we have a separate variable for the actions, which is the activated output of the network, and we're going to use a softmax so that way we get probabilities that add up to 1. We need to calculate the negative log probability with a sparse softmax cross entropy function with logits, using dense2 as our logits and labels as the actions as our labels. The loss is just that quantity multiplied by the expected future rewards. And of course we want to reduce that quantity. Now for the training operation, we're going to use the RMS prop optimizer with a set of parameters. I found these to work quite well. This algorithm is pretty finicky, so you may have to play around. The next thing we have to do is code up the action selection algorithm for the agent. In policy gradient methods, we're trying to actually approximate the policy, which means we're trying to approximate the distribution by which the agent chooses actions given it's in some state S. So what we need is a way of computing those probabilities and then sampling the actions according to those probabilities. We choose an action by taking in an observation, reshaping it. Of course, this will be a sequence of frames 4 high. And you want to calculate the probabilities associated for each action given that observation. And then you want to sample that probability distribution using the numpy random choice function. Next up, we have to take care of the agent's memory. So we're going to store the observation, action, and reward in the agent's list using a simple append function. So one big problem we're going to have to solve is the fact that policy gradient methods are incredibly sample inefficient. These Monte Carlo methods, meaning that at the end of every episode, the agent is learning. So it throws away all of the experience it required in prior episodes. So how do we deal with that? Well, one way to deal with that is to actually queue up a batch of episodes and learn based on that batch of experiences. The trouble here is that when we take the rewards that follow any given time step, we don't want to account for rewards following the current episode. So we don't want rewards from one episode spilling over into another. So we have to take care of that here. Next up, we handle the learning for the agent. We want to convert the state, action, and reward memories into arrays so that we can feed them into the TensorFlow learning function. Into the TensorFlow graph. We have to start by reshaping the state memory into something feasible, and then we can calculate the expected future rewards starting from any given state. So what we're going to do is iterate over the entire memory and take into account the rewards the agent receives for all subsequent time steps. We also need to make sure that we're not going to take into account rewards from the next episode. Next up, we have to scale the expected future rewards. This is to reduce the variance in the problem. So this makes sure we don't have really, really large rewards, so everything is just kind of scaled. Next up, we call the training operation with an appropriate feed dict of the state memory, action memory as labels, and the G for our G variable. Finally, since we're done, we're going to clear out the agent's memories. Finally, we just have some bookkeeping functions to load and save checkpoints. These just call the saver restore function that loads the checkpoint file into the session, and the save checkpoint just dumps the current session into the checkpoint file. Another problem we have to solve is that the agent doesn't get a sense of motion from only a single image, right? If I show you a single image, you don't know if the aliens are moving left or right, or really you don't know which direction you're moving. So we have to pass in a sequence of frames to get a sense of motion for our agent. This is complicated by the fact that the OpenAI Gym Atari library in particular returns a set of frames that are repeated. So if you actually cycle through the observations over time, you'll see that the frames don't change based on an interval of 1, 2, or 3. So we have to capture enough frames to account for that fact, as well as to get a overall sense of movement. So that means 4 is going to be our magic number for stacking frames. Next, we move into the main program where we import Gym, NumPy, our model, as well as the plot learning function, which is a simple utility you can find on my GitHub, as well as the wrappers to record the agent's gameplay if you so choose. We need to pre-process the observation by truncating it and taking the average. Next up, we stack the frames. So at the beginning of the episode, stacked frames will be none. So you want to initialize an empty array of zeros and iterate over that array and set each of those rows to be the current observation. Otherwise, what you want to do is you want to pop off the bottom observation, shift everything down, and put the fourth spot or the last spot to be the current observation. Down in the main function, we have a checkpoint flag. If we want to load a checkpoint, we want to initialize our agent with this set of hyperparameters. I found these to work reasonably well. You can play around with them, but it is incredibly finicky, so your mileage may vary. We need a file name to save our plots. We'll also want to see if we want to load a checkpoint. Next, we initialize our environment, Space Invaders, of course. Keep track of his score history, score, number of episodes, and our stack size of 4. Want to iterate over the number of episodes, resetting the done flag at the top of each episode. We also want to keep track of the running average score from the previous 20 games, just so we get an idea if it's actually learning. Every 20 games, we're going to print out the episode score and average score. Otherwise, every other episode, we're just going to print out the episode number and the score. Reset the environment, and of course you have to pre-process that observation, and then go ahead and set your stacked frames to none because we're at the top of the episode, and then call the stack frames function so that we get 4 of the initial observation. Set the score to 0 and start iterating over the episode. So his first step is to choose an action based on that set of stacked frames. Go ahead and take that action and get your new state, action, and reward. Go ahead and pre-process that observation so that way you can stack it on the stack of frames. Next up, you have to take care of the agent's memory by storing that transition. And finally, you can increment your score, save the score at the end of the episode, and every 10 games we're going to handle learning and saving a checkpoint. And when you're all done, go ahead and plot the learning. Now that the agent is done, we can take a look at the actual plot it produces over time. This is how you know an agent is actually learning. What you'll see is that there is some increase in the average reward over time. You'll see oscillations up and down, and that's perfectly normal, but what you want is an overall upward trend. Now, for this particular set of algorithms, it is notoriously finicky with respect to learning rates. I didn't spend a huge amount of time tuning them or playing with them. I just wanted to get something good enough to show you guys how it works and turn it over to your capable hands for fine tuning. But what you do see is a definite increase over time as the agent's average reward improves by about 100 points or so. That isn't going to win any awards, but it is definitely a clear and unequivocal sign of learning. So there you have it. That was policy gradients in the Space Invaders environment from the OpenAI gym. I hope you learned something. Make sure to check out this code on my GitHub. You can fork it, you can copy it, you can do whatever you want with it. Make sure to subscribe, leave a comment down below if you found this helpful, and I look forward to seeing you all in the next video. Welcome back, everybody, to NeuralNet.ai. I am your host, Phil Tabor. Previously, a subscriber asked me, "Hey Phil, how do I create my own reinforcement learning environment?" I said, well, that's a great question. I don't have time to answer it in the comments, but I can make a video, so here we are. What we're going to do in the next 2 videos is create our own OpenAI Gym compliant reinforcement learning environment, the Grid World. It's going to be text-based, and if you're not familiar with it, the Grid World is aptly named a grid of size n by n, where the agent starts out in, say, the top left, and has to navigate its way all the way to the bottom right. The twist on this is going to be that there will be 2 magic squares that cause the agent to teleport across the board. The purpose of doing this is to create a shortcut to see if the agent can actually learn the shortcut. Kind of interesting. The agent receives a reward of -1 with each step except for the terminal step, where it receives a reward of 0. Therefore, the agent will attempt to maximize its reward by minimizing the number of steps it takes to get off the grid world. What other things? 2 other concepts we need are the concept of the state space, which is the set of all states minus the terminal state, and the state space plus, which is the set of all states including the terminal state. This gives us a bit of a handy way to find out the terminal state, as well as to find out if we're attempting to make illegal moves. It also follows the nomenclature and terminology from the Sutton and Bardo book, Reinforcement Learning, which is an awesome resource you should definitely check out if you have not already. So in part 1, we're going to handle the environment, and in part 2, we're going to get to the main loop and the agent, for which we will use Qlearning. Not deep Qlearning, because this is a very straightforward environment. We don't need a functional approximation. We just need the tabular representation of the agent's estimate of the action value function. So if you're not familiar with Qlearning, I do have a couple videos on the topic. One where the Qlearning agent solved the card pull game, as well as an explainer type video that talks about what exactly Qlearning is. So let's go ahead and get started. We only have a couple dependencies We're not doing anything on the GPU, so just numpy and matplotlib. We want to close everything up into a class called grid world, and our initializer will take the M and N, which is the shape of the grid, as well as the magic squares. So we represent our grid as an array of zeros in shape M by N. We want to learn to type. We want to learn to. Sorry, we want to keep track. We want to keep track of the M and the N for handy use later. So let's go ahead and define our state space, and that's just going to be a list comprehension for all the states in the range self.m times self.n. Now, as I said, the state space does not include the terminal state, and the terminal state is the bottom right, so we have to go ahead and remove or pop off that particular state from the list. Next up. So now let's go ahead and again learn to type. Go ahead and define our state space plus. Also, we need to know the way that the actions map up to their change on the environment. So we'll call that the action space. A little bit of a misnomer, but we can live with it for now. So moving up will translate the agent up one row, which is distance m, and moving down will advance the agent's position downward by also m. Moving left will translate the agent one step, will decrement the agent's position by 1, and moving right will increase it by 1. We also want to keep track of the set of possible actions. You could use the keys in the action space dictionary, but let's go ahead and use a separate structure, and we'll use a list up, down, left, and right. The reason is that the Qlearning agent, the Qlearning algorithm, sorry, can choose actions at random, so it is handy to have a list from which you can choose randomly. Next, we need to add the magic squares, because that's a little bit more complicated than it may seem. And finally, when we initialize the grid, we want to set the agent to the top left position. Let's go ahead and add those magic squares. So, of course, we want to store that in our object. Now, there's a little bit of hokiness that I must explain. So, the agent is represented by a 0 when we print out the grid to the terminal, and empty squares are represented by a 1. And so, and so that means we need something other than 0 and 1 to represent these magic squares. When I render the environment, I want to know where the entrance and where the exit is. So we use different values for the entrance and exit, so that way we can render it correctly. So just by royal decree, we set I, which will be the representation of the magic square in the grid world, to 2 to start. And we're going to go ahead and iterate over the magic squares. So now what we need to know is what position we are in. So the color is off, indicating something is wrong. I have screwed something up royally, which I do not see because I am blind. Anyway, so the X position is just going to be the floor of the current square and the number of rows, and Y will be the modulus of the number of columns. So then the grid, we want to set that X and Y position to I. And since we want to have a different representation for the entrance and exit, go ahead and set the increment I by 1. Recall that the magic squares is represented as a dictionary, so we're iterating over the keys, and the values are the destinations. So the keys are the source, values are destinations. So next we want to find out precisely that, what the destinations are. So .n, and then set the grid, that square, to I, and then increment I again. And I'm only going to do 2 magic squares. You can do any number, but in this case we're just going to do 2. So okay, so the next thing we need to know is if we are in the terminal state. And as I said earlier, the state space and state space plus concepts give us a very easy way of doing that. So let's go ahead and take care of that. So since the state space plus is all of the states and the state space is all of the states minus the terminal state, we know that the difference between these two sets is the terminal state. So state in state space plus and not in the state space. How does that look? Let me scroll down a bit. Okay. So next up, let us go ahead and get the agent row and column. And we're going to use the same logic as above. So next we want to set the state. So that will take the new state as input. And we're going to go ahead and assume that the new state is allowed. So the agent, if it is along the left edge and attempts to move left, it just receives a reward of -1 and doesn't actually do anything. Likewise, if it's on the top row and attempts to move up, it doesn't actually do anything. It just gets a reward of -1 for wasting its time. So we want to get the row and column and set that space to 0 because 0 denotes an empty square. And the agent position then is the new state. And again, we want to get the new X and new Y. There is a typo there. Let's fix that. And then set that position to 1 because that is how we represent the agent by royal decree. So the next thing we have to know is if we're attempting to move off the grid. That's not allowed. The agent can only stay on the grid, so let's take care of that. So we want to take the new and old states as input. And the first thing we want to know is if we're attempting to move off the grid world entirely. So I hate these editors. So if the new state is not in the new state space plus, we are attempting to move off the grid, so you return true. Otherwise, if the old state modulus m equals 0 and new state modulus self.m equals self.m minus 1, then we return true. And for brevity, I could explain this, but the video is running long already. So for brevity, the reason this is true is left as an exercise to the reader. Bet you didn't know this was going to be like a college course. So now basically what we're trying to do here, I'll just give you a hint. What we're trying to do here is determine if we're trying to move off the grid either to the left or to the right. We don't want to wrap around. So if you're, for instance, if we have a 9x9 grid, it goes from 0 to 8. So then if you add 1, right, you would get 9, which would teleport you to the other row in the 0th column. You don't want that. What you want to do is waste a move and receive a reward of -1. So that's what we're doing here. Old state modulus. Good grief. So if neither of those are true, then you can go ahead and return false, meaning you're not trying to move off the grid. So let's see, can you see that? You can. So next function we need is a way to actually step. So let's go ahead and do that. Let's say the only thing we need is to take in the action. So the first thing you want to do is get the X and Y again. And here's where we're going to check to make sure it's a legal move. So the resulting state is then agent position plus the mapping. So the agent position is whatever it is, and recall that the action space is this dictionary here that maps the actions to their translations in the grid. So what we're doing down here then is saying the new state is equal to the current state plus whatever the resulting translation is for whatever action we're attempting to make. So next thing we need to know is, are we on a magic square? And if we are, then the agent teleports to its new position. Okay, so next up we need to handle the reward. So it's -1 if not is terminal state. So it's -1 if we haven't transitioned into the terminal state, otherwise it is 0. If we're not trying to move off the grid, then we can go ahead and set that state. Self.set state, resulting state, and then we're ready to go ahead and return. So in the OpenAI gym, whenever you take a step, it returns the new state, the reward, whether or not the game is over, and some debug information. So we're going to do the same thing. Resulting state, reward, and the whether or not it is the terminal state, and our debug info is just going to be none. So if we are attempting to move off the grid, what do we want to do? Nothing. So we want to return agent position and the reward and whether or not it's terminal and the null debug info. We're almost there. So next thing we need to know is how do we reset the grid? Because at the end of every episode we have to reset, right? First thing to do is set the agent position to 0. Reset the grid to zeros. And go ahead and add the magic squares back in. and return the agent position, which is of course 0. Oh wow, that's real close. All right, so next up, one last function. I swear, just one more, I promise. All right, I wouldn't lie to you. All right, next up, we want to provide a way of rendering because, hey, that's helpful for debug. I like to print a whole big string of, dashes because it's pretty. We want to iterate over the grid for column and row. Column equals 0. In other words, if it's an empty square, we're just going to print a dash, and we're going to end it with a tab. If the column is 1, meaning we have an agent there, we're going to print an X to denote the agent. Now, if the column is 2, then that is one of the entrances to our magic squares. So print the A in with a tab delimiter, a tab end. If the column equals 3, you can print A out and equals tab. And if the column equals 4, then we know we're at the other magic square entrance. And finally, if it's 5, then we know we're at the other magic square's exit. After each row, we want to print a new line. And at the end, we'll go ahead and print another chunk of pretty dashes. Oh. Yeah, that's it. That is it. Okay, so that is it for our agent class. That only took, how long? 20-some minutes. Wow. Okay. I hope you're still with me. Basic idea here is to make your own environment, you need an initialize, a reset, a state space plus, a way to denote possible actions, a way to make sure the move is legal, and a way to actually affect that environment. The step function needs to return the new position, the reward, whether or not the new state is terminal, as well as some debug information. You also need a way of resetting and printing out your environment to the terminal. So in part 2, we're actually going to fire this baby up with a Qlearning algorithm and see how she do. That's actually quite exciting. Moderately exciting anyway. It actually learns, it does quite well, and it does find the magic square. Spoiler alert if you made it this far. It finds a magic square and gets out the minimum number of moves required. It's pretty cool to see, so that will come in the next video on Wednesday. I hope to see you all then. If you liked the video, make sure to leave a thumbs up. Subscribe if you have not already for more reinforcement learning content, and I will see you all in the next video. Welcome back, everybody, to a new tutorial from neuralnet.ai. I'm your host, Phil Tabor. If you're new to the channel, I'm a physicist, former semiconductor process engineer turned machine learning practitioner. If you haven't subscribed yet, go ahead and hit the subscribe button so you don't miss any future reinforcement learning tutorials. When we left off in our previous video, we just finished up the bulk of our OpenAI Gym compliant reinforcement learning environment. Today we're going to go ahead and code up a Qlearning agent and the main loop of the program to see how it all performs. So let's go ahead and get started. So the first thing we are going to need is the magic squares, right? If you recall, the magic squares are the teleporters in the grid world that either advance the agent forward or backward. So the first one is going to be at position 18 and dump out at position 54, so it'll move it forward. And the next one will be at, let's say, 63 and dump out at position 14. So teleporter A will advance the agent through the grid world, and teleporter B will send it back to an earlier square. So we need to create our grid world. We use a 9x9 grid and pass in the magic squares we just created. Next up, we have to worry about the model hyperparameters. So if you are not familiar with that, let me give you a quick rundown. These are the parameters that control how fast the agent learns and how much it chooses to value the potential future rewards. So the first parameter is alpha. That is our learning rate. 0.1. A gamma of 1.0 tells us that the agent is going to be totally farsighted. It will count all future rewards equally. An epsilon of 1.0, this is of course the epsilon for epsilon greedy action selection. So it will start out behaving pretty much randomly and eventually converge on a purely greedy strategy. So Qlearning is a tabular method where you have a table of state and action pairs, and you want to find the value of those state action pairs. So to construct that, we have to iterate over the set of states and actions. State space plus and env.possible actions. And you have to pick something for an initial value. It's really arbitrary, but the cool thing about picking 0 is that we're using something called optimistic initial values. What this means is that since the agent receives a reward of -1 for every step, it can never have a reward of 0, right? Because there's some distance between the agent and the exit. So by setting the initial estimate at 0, you actually encourage exploration of unexplored states, because if the agent takes a move, it realizes, oh, I get a reward of -1, that's significantly worse than 0. Let me try this other unexplored option. So over time, it will gradually explore all the available actions for any given state, because it's been disappointed by all the stuff it has previously tried. Just a fun little fact. We want to play 50,000 games. We need a way of keeping track of our rewards. NumPy array will do just fine, yes? So now let's iterate over the total number of games. And I like to print out a marker to the terminal so that way I know it's actually working. So if every 5,000 games, just print that we're starting the ith game. At the top of every episode, you want to reset your done flag. You want to reset your episode rewards so you don't accumulate rewards from episode to episode. And of course, you want to reset your environment. Oh, let me scroll down here. There we go. You want to reset your environment just as you would with any OpenAI Gym type problem. Next up, we begin each episode. So while not done, we want to take a random number for our epsilon greedy action selection. So we're going to just make use of this max action before we define it. Q, observation, and env.possible actions. And what that will do is, we're going to write it here momentarily, but what it's going to do is it is going to find the maximum action for a given state. So if the random number is less than 1 minus epsilon, we want to do that. Can you guys see that? Yep. Otherwise, we want to take a random sample of the action space. So we have to write these two functions. Let's do that quite quickly. So the action space sample is pretty straightforward. We can just return a random choice from the list of possible actions. And that's the reason we chose a list as that data structure, just to make it easy. Next up, we have the max action function, but that doesn't need to belong to the class. That takes the queue, the state, and the set of possible actions. We want to take a numpy array of the estimates agent the agent's estimate of the present value of the expected future rewards for the state it's in and all possible actions. A in actions, and then we want to find the maximum of that. And that's just an index, so we want, that's just an index, so we want to return the action that actually corresponds to. All right, that's all well and good. Do we need more space? Let's do a little bit more. There we go. So next, we want to actually take the action. So we get our new state, observation underscore, reward, done, and info. env.step action. And next up, we have to calculate the maximal action for this new state so that we can insert that into our update equation for the Q function. So let's do that. And we're not worried about epsilon greedy here because we're not actually taking that action. Next up, we have to update our Q function for the current action and state. And that's where our alpha comes in. Word plus, make sure that is visible to you. Reward plus some quantity, which is gamma, our discount factor, times Q, observation underscore, action underscore, so the new state and action, minus Q observation action. Let me tab this over. There we go. Nice and compliant with the PEP style guides, right? Mostly. Okay, so this is the update equation for the Q function. That will update the agent's estimate of the value of the current state and action pair. Next up, we just need to let the agent know that the environment has changed states, so you set observation to observation underscore. And that is it for Qlearning in a nutshell, folks. That's really that straightforward. So at the end of each episode, we want to decrease epsilon. So that way the agent eventually settles on a purely greedy strategy. You can do this a number of ways. You can do it, with a square root function, a log function. I'm just going to do it linearly. It's not that critical for something like this. So it's going to decrease it by 2 divided by num games every game, so about halfway through it'll be purely greedy. And at the end of every episode, you want to make sure you're keeping track of the total rewards, which is something I forgot up here. Yeah, so one thing I did forget is to keep track of the total reward for the episode. Don't forget that, very important. And at the end of all the episodes, you want to plot the total rewards. And that is it for the coding portion. Oh, one other thing, I take it back. So let's scroll up here. I do want to show you the environment, so let's just do that, env.render. And the purpose of doing that is so that you can see how many moves it takes the agent to escape from the grid world. That will tell us if it's doing good or not, right? Because there's a minimum number of moves it takes to escape. So I'm going to fire up the terminal and go ahead and get that started. 1 second. And here we are in the terminal. Let's go ahead and run that. And you can see here that we start at the top left. So it takes 1, 2, moving to A out is free. So 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, 11. And the 12th move is free because it's the exit to the maze. Sorry, to the grid world. So total reward of minus 11 is the best the agent can possibly do. It's gone ahead and plotted, so let's check that out. And here is the plot. And you can see that indeed the agent starts out rather poorly, exploring, finding suboptimal routes through the grid world. But eventually, and about halfway through here at 2500 or so, 25,000, you can see that it settles on at least a constant value. Let's prove that it is the maximal value of minus 11, and you can see that it's 10.97. That is close enough for government work. So you see that the agent is able to actually solve the maze, the grid world, I keep calling it a maze, is able to solve the grid world using the Qlearning algorithm. Now this isn't surprising, we would expect this. What's novel here is that we have created our own reinforcement learning environment that uses a very similar format to the OpenAI Gym. So anytime you want to create a new environment, you can fire this video up and use the set of code here just as a template for your own projects. I'm going to put this up on my GitHub. I'll link that down below, and I'm also going to write up a tutorial in text form and upload it to neuralnet.ai. I don't know if I'll have that done tonight. I'll update the description with it. And that's if you are if you consume text more easily than video, then you can go ahead and check that out. I hope this has been helpful. Make sure to leave a comment, subscribe if you haven't already, and I hope to see you all in the next video.
Welcome back, data manglers. Thanks for tuning in for another episode from neuralnet.ai. If you're new to the channel, I'm Phil Tabor, a physicist and former semiconductor engineer turned machine learning practitioner. I'm on a mission to teach the next generation of data engineers so we can stay one step ahead of our robot overlords. If you're not subscribed, be sure to do that now so you don't miss any future reinforcement learning content. We've touched on reinforcement learning many times here on the channel, as it represents our best chance at developing something approximating artificial general intelligence. We've covered everything from Monte Carlo methods to deep Qlearning to policy gradient methods using both the PyTorch and Tensorflow frameworks. What we haven't discussed on this channel is the what and the how of reinforcement learning. That oversight ends today, right now. Okay, maybe a few seconds from now, but either way, we're going to cover the essentials of reinforcement learning. But first, let's take a quick step back. You're probably familiar with supervised learning, which has been successfully applied to fields like computer vision and linear regression. Here, we need mountains of data, all classified by hand, just to train a neural network. While this has proven quite effective, it has some pretty significant limitations. How do you get the data? How do you label it? These barriers put many of the most interesting problems in the realm of megacorporations, and this does us, the individual practitioners, no good. To top it off, it's not really intelligence. You and I don't have to see thousands of examples of a thing to understand what that thing is. Most of us learn actively by doing. Sure, we can shortcut the process by reading books or watching YouTube videos, but ultimately we have to get our hands dirty to learn. If we abstract out the important concepts here, we see that the essential stuff is the environment that facilitates our learning, the actions that affect that environment, and the thing that does the learning, the agent. No jacket or labels required. Enter reinforcement learning. This is our attempt to take those ingredients and incorporate them into artificial intelligence. The environment can be anything from text-based environments like card games, to classic Atari games, to the real world. At least, if you're not afraid of Skynet starting an all-out nuclear war, that is. Our AI interacts with this environment through some set of actions, which is usually discrete. Move in some direction or fire at the enemy, for instance. These actions in turn cause some observable change in the environment, meaning the environment transitions from one state to another. So for example, in the Space Invaders environment in the OpenAI Gym, attempting to move left caused the agent to move left with 100% probability. That need not be the case though. In the Frozen Lake environment, attempting to move left can result in the agent moving right, or up, or down even. So just keep that in mind that these state transitions are probabilistic and the probabilities don't have to be 100%, merely their sum. The most important part of the environment is the reward or penalty the agent receives. If you take only one thing away from this video, it should be that the design of the reward is the most critical component of creating effective reinforcement learning systems. This is because all reinforcement learning algorithms seek to maximize the reward of the agent. Nothing more, nothing less. In fact, this is where the real danger of AI is. It's not that it would be malicious, but that it would be ruthlessly rational. The classic example is the case of an artificial general intelligence whose reward is centered around how many paperclips it churns out. Sounds innocent, right? Well, if you're a paperclip making bot and you figure out that humans consume a bunch of resources that you need to make paperclips, then those pesky humans are in the way of an orderly planetary scale office. That's problematic for all involved. What this means is we must think long and hard about what we want to reward the agent for, and even introduce penalties for undertaking actions that endanger human safety, at least in systems that will see action in the real world. Perhaps less dramatic, although no less important, are the implications for introducing inefficiencies in your agent. Consider the game of chess. You might be tempted to give the agent a penalty for losing pieces, but this would potentially prevent the agent from discovering gambits, where it sacrifices a piece for a longer-term positional advantage. The AlphaZero engine, a chess-playing artificial intelligence, is notorious for this. It will sacrifice multiple pawns and yet still dominate the best traditional chess engines we have to offer. So we have the reward, the actions, and the environment. What of the agent itself? The agent is the part of the software that keeps track of these state transitions, actions, and rewards, and looks for patterns to maximize its total reward over time. The algorithm that dictates how the agent will act in any given situation or state of the environment is called its policy. It is expressed as a probability of choosing some action A given the environment is in some state S. Please note, these probabilities are not the same as the state transition probabilities. The mathematical relationship between state transitions, rewards, and the policy is known as the Bellman equation, and it tells us the value, meaning the expected future reward of a policy for some state of the environment. Reinforcement learning often, though not always, means maximizing or solving that Bellman equation. More on that in future videos. This desire to maximize reward leads to a dilemma. Should the agent maximize its short-term reward by exploiting the best known action, or should it be adventurous and choose actions whose reward appears smaller or maybe even unknown? This is known as the explore-exploit dilemma, and one popular solution is to choose the best known action most of the time, and occasionally choose a suboptimal action to see if there's something better out there. This is called an Epsilon greedy policy. When we think of reinforcement learning, we're often thinking about the algorithm the agent uses to solve the Bellman equation. These generally fall into two categories: algorithms that require a full model of their environment and algorithms that don't. What does this mean exactly, to have a model of the environment? As I said earlier, actions cause the environment to transition from one state to another with some probability. Having a full model of the environment means knowing all the state transition probabilities with certainty. Of course, it's quite rare to know this beforehand, and so the algorithms that require a full model are of somewhat limited utility. This class of algorithms is known as dynamic programming. If we don't have a model, or our model of the environment is incomplete, we can't use dynamic programming. Instead, we have to rely on the family of model-free algorithms. One popular such algorithm is Qlearning or deep Qlearning, which we studied on this channel. These rely on keeping track of the state transitions, actions, and rewards to learn the model of the environment over time. In the case of Qlearning, these parameters are saved in a table, and in the case of deep Qlearning, the relationships between them are expressed as an approximate functional relationship, which is learned by a deep neural network. That's really all there is, at least at a high level. So to recap, reinforcement learning is a class of machine learning algorithms that help an autonomous agent navigate a complex environment. The agent must be given a sequence of rewards or penalties to learn what is required of it. The agent attempts to maximize this reward over time, or in mathematical terms, to solve the Bellman equation. The algorithms that help the agent estimate future rewards fall into two classes: those that require we know the state transition probabilities for the environment beforehand, and those that don't. Since knowing these probabilities is a rare luxury, we often rely on model-free algorithms like DBQ Learning. If you'd like to know more, please check out some of the other videos on this channel. I hope this has been helpful. Please leave a comment, a like, and subscribe if you haven't already. Look forward to seeing you all in the next video. Welcome back to the free reinforcement learning course from neuralnet.ai. I'm your host, Phil Tabor. If you're not subscribed, be sure to do that now and hit the bell icon so you get notified for each new module in the course. In Module 1, we covered some essential concepts in reinforcement learning, so if you haven't seen it, go ahead and check it out now so this module makes more sense. If you have seen it, you may remember that reinforcement learning basically boils down to an agent interacting with some environment and receiving some rewards in the process. These rewards tell the agent what's good and bad, and the agent uses some algorithm to try to maximize rewards over time. In practice, what we get is a sequence of decisions by the agent, and each decision doesn't just influence its immediate reward, rather each decision influences all future rewards. In mathematical terms, we have a sequence of states, actions, and rewards that one could call a decision process. If each state in this process is purely a function of the previous state and action of the agent, then this process is called a Markov decision process, or MDP for short. These are an idealized mathematical abstraction that we use to construct the theory of reinforcement learning. For many problems, this assumption can be broken to various degrees. How much that really matters is often a complicated question and one we're just going to dodge for now. Regardless, in most cases, the assumption that a process obeys the Markov property is good enough, and we can use all the resulting mathematics for reinforcement learning problems. By now, I've said that a reinforcement learning agent seeks to maximize rewards over time. So how does this fit into a Markov decision process? From the agent's perspective, it receives some sequence of rewards over time, and that sequence of rewards can be used to construct the expected return for the agent. Then, the return at some time step t is just the sum of the rewards that follow all the way up to some final time, capital T. This final time step naturally introduces the concept of episodes, which are discrete periods of gameplay that are characterized by state transitions, actions, and rewards. Upon taking this final time step, the agent enters some terminal state which is unique. This means that no matter how we end the episode, the terminal state is always the same. No future rewards follow after we reach the terminal state, so the agent's expected reward for that terminal state is precisely 0. With a bit of creativity, we call tasks that can be broken into episodes episodic tasks. Of course, not all tasks are episodic. Many are in fact continuous. This is a bit of a problem, since if the final time step is at infinity, the total reward could also be infinite. This makes the concept of maximizing rewards meaningless, so we have to introduce an additional concept. The fix, and we use this for both episodic and continuing tasks, is the idea of discounting. This basically means the agent values future rewards less and less. This discounting follows a power law where each time step results in more and more discounting. This hyperparameter gamma is called the discount rate, and you've no doubt seen this before in our videos on reinforcement learning. If you use this form for the expected return and do some simple factoring, you derive a really useful fact. There is a recursive relationship between rewards at subsequent time steps. This is something we'll exploit constantly in reinforcement learning. So, we have an agent that is engaged in some discrete processes, receiving rewards and trying to maximize its expected future returns. If you remember from the first lecture, the algorithm that determines how the agent is going to act is called its policy. Since the agent has a set of defined rules for how it's going to act in any given state, it can use a sequence of states, actions, and rewards to figure out the value of any given state. The value of a state is the expected return when starting in that state and following the policy. It's given formally by the following equation. In some problems, like say Qlearning, we're more concerned with maximizing the action value function, which tells the agent the value of taking some action while in some given state and following the policy thereafter. Remember how I said we can exploit the recursive relationship between subsequent returns? Well, if we plug that into the expression for the value function, we actually discover that the value function itself is defined recursively. This is called the Bellman equation from the first module, and this is the quantity many algorithms seek to maximize. The Bellman equation is really an expectation value, as it's a weighted average of how likely each particular sequence of states, actions, and rewards is, given the state transition probabilities and the probability of the agent selecting that action. Much of the following material will involve coming up with various schemes to solve the Bellman equation and evolve the policy in such a way that the value function increases over time. In the next module, we'll take a look at the explore-exploit dilemma, which is the expression of the trade-off between long and short-term rewards. I hope this has been helpful. Questions, comments, suggestions, leave them below. I read and answer all my comments. If you made it this far, consider subscribing so you get notified when the rest of the course drops. I look forward to seeing you in the next video. Welcome to Module 3 of the free reinforcement learning course from neuralnet.ai. I'm your host, Phil Tabor. If you're not subscribed, make sure to do that now so you don't miss the rest of the course. In the previous video, we learned about a special type of process called the Markov decision process. There, each state depends only on the previous state and the action taken by the agent. This leads to the recursive relationship between the agent's estimate of returns at successive time steps. This relationship extends to the agent's estimate of the value function, which is given by the Bellman equation. As we covered in Module 1, reinforcement learning, for the most part, boils down to maximizing this value function. However, it's not always so simple. Surprise, surprise. Just like you and I have trade-offs in real life, reinforcement learning agents are faced with similar considerations. Should the agent take the action that it knows will immediately provide the most reward, or should it explore other actions to see if it can do better? This conundrum is known as the explore-exploit dilemma, and every reinforcement learning algorithm has to deal with this. Fortunately, there are many solutions, and we'll cover some of them here. One such solution is the idea of optimistic initial values. When the agent starts playing the game, it has to use some initial estimate for the value or action value function. This estimate is totally arbitrary, but if we know something about the reward structure beforehand, we can actually initialize it in such a way as to encourage exploration. Suppose we have an environment like our grid world in the video on creating our own reinforcement learning environment. In that environment, the agent receives a reward of -1 for each step, and so the expected returns are always negative or 0, no matter of the state of the environment or the action the agent takes. So what would happen if we tell the agent that the value of all the state action pairs are positive or even 0? On the first move, the agent picks some action randomly because all the actions look identical. It receives a reward of -1 and updates its estimates accordingly. So it's a bit disappointed. It was expecting chocolate cake and got a mud pie. The next time it encounters that state, it will take a different action because the other actions have an estimate of 0 reward for that state, which is better than the negative reward it actually received. This means that the agent ends up exploring all the state action pairs many times as each update makes the agent's estimate more and more accurate. We never had to explicitly tell the agent to take exploratory actions because its greed drove it to take exploratory actions after it became disappointed with whatever action it just took. Again, this is called optimistic initial values. Another feasible solution is to spend some portion of the time choosing random actions and the majority of the time choosing greedy actions. This is called an Epsilon greedy strategy, and it's the one we employ the most. It's quite robust as we can change the random parameter over time so that the agent converges onto a nearly pure greedy strategy. The proportion of the time the agent spends exploring is a hyperparameter of the problem, and we typically call it Epsilon. One potential strategy is to start out completely randomly and then use some decay function to gradually increase the proportion of greedy actions the agent takes. The form of this function isn't critically important. It can be linear, a power law, or really any other function. Whether or not the agent converges to a purely greedy strategy is going to depend on the problem. For simple environments like the grid world, where we know the optimal solution beforehand, it makes quite a bit of sense to converge to a purely greedy strategy. However, with a game like Space Invaders, a popular environment from the OpenAI gym, there are so many variables that it's hard to be sure the agent has settled on the truly optimal strategy. The solution there is to leave Epsilon at some small but finite value so the agent is occasionally taking exploratory actions to test its understanding of the environment. All of this discussion has made a very important assumption. We've assumed the agent only uses a single policy. The agent uses both the same policy to update its estimate of the value function as well as to generate actions. There's no rule this has to be the case. In fact, an agent can leverage two policies. It can use one policy to generate actions and then use the data that generates to update the value function for some other policy. This is called off-policy learning, and this is precisely what we use in Qlearning. The agent uses some Epsilon greedy strategy to generate steps in the Markov chain, which is the sequence of state, action, rewards, and resulting states, and then uses that data to update the estimate of the action value function for the purely greedy action. In effect, we're using an Epsilon greedy strategy to update our estimate of the purely greedy strategy. Needless to say, this works quite well, and it's something we'll come back to in later modules when we get to Monte Carlo methods and temporal difference learning. That's it for now. Reinforcement learning agents seek to maximize their total reward, but face a dilemma of whether to maximize current reward or take exploratory steps with suboptimal actions in the hope of optimizing long-term rewards. One solution is to bias the agent's initial estimates in such a way that it encourages exploration before settling on a purely greedy strategy. Another is to spend some proportion of the time exploring and the majority of the time exploiting the best known action. And finally, the agent can leverage two policies, one to generate data and the other to update the estimate of the action value or value function. In the next module, we're going to get to dynamic programming, class of model-based reinforcement learning algorithms. Make sure to subscribe so you don't miss the remainder of this course, and I look forward to seeing you in the next video.
Welcome back, everybody, to Machine Learning with Phil. I am your host, Dr. Phil. When we last touched on the OpenAI gym, we did Qlearning to teach the cart pole robot how to dance, basically, how to balance the pole. In this video, we're going to take a look at a related algorithm called SARSA. So they're related in the sense that they're both types of temporal difference learning algorithms, the difference being that SARSA is an on-policy method and Qlearning is an off-policy method. Hey, appearance by the cat. If you don't know what that means, I highly encourage you to check out my course, Reinforcement Learning in Motion, on Manning Publications. I go in depth on all of this stuff in that course. Enough plugging, let's get back to it. So the other cool thing is that SARSA, as well as Qlearning, are model-free, meaning that you do not need a complete model of your environment to actually get some learning done. And that's important because there's many cases in which you don't know the full model of the environment. What does that mean? It means you don't know the state transition probabilities. So if you're in some state S and take some action A, what is the probability you will end up in state S prime and get reward R? Those probabilities are not completely known for all problems, and so algorithms that handle that uncertainty are critical for real-world applications. Another neat thing is that this is a bootstrapped method, meaning that it uses estimates to generate other estimates, right? So you don't need to know too much about the system to get started. You just make some wild-ass guesses and you get moving. Let's take a look at the algorithm. So your first step is to initialize your learning rate alpha. And of course, that's going to control the rate of learning, how quickly you make adjustments to the Q function. Then you initialize the Q function. The Q function is just the agent's estimate of its discounted future rewards starting from a given state S and taking an action A. And it may have some assumptions built in onto whether or not you follow some particular policy or not, but that's the general gist. So you need to initialize your state and choose some initial action based on that state using an epsilon greedy strategy from that function Q. Then you loop over the episode, take the action, getting your reward and your new state S prime, choose an action A prime as a function of that state S prime. using epsilon greedy from your Q function, and then go ahead and update the Q function according to the update rule you see on the screen, and then go ahead and store your state prime into S and your A prime into A, and loop until the episode is done. Again, in the course I go into many more details. This is just quick and dirty, a bit of a teaser video to get you guys interested in the course and to give you some useful information at the same time. So with that being said, let's go ahead and jump into the code. I'm not going to be doing typing on screen, but I will be showing you the relevant code as we go along. And boom, we are back in the code editor. So here I am using Visual Studio Code. Even on Linux, this is a great editor. If you're not using it, I highly recommend it. Atom was a little bit buggy for me, and of course Sublime is Nagware. So go ahead and give it a look if you haven't already. So we need to define a function to take the max action, and that takes as inputs the Q function as well as the state. And you're just converting the Q function into an array, into a numpy array for each action in that list, and finding the argmax of that. Now recall that in numpy the argmax returns the first element of a max. So if you have two actions that are tied, it'll give you the first one. So of course in the cart pole example, our action space is just moving left and right. If you don't remember, it's just a cart that slides along the x-axis trying to keep a pole vertical. Of course, this is a continuous space, and the Q function is a discrete mathematical construct, right? So the states are discrete numbers, and so you have to do a little trick here to discretize your space. And so if you look in the documentation for the cart pole example, you'll find the limits on these variables, and you can use that to create a linear space based out of it, based on those limits, and divide it up into 10 different buckets, right? So that way you get, you go from a continuous representation to a discrete representation of your state space. And then I define a small helper function here to get the state based on the observation. It just digitizes these, it digitizes those linear spaces using the observation that you pass in from the OpenAI gym. And it returns a 4 vector that is the buckets that correspond to the value of the element of the observation. In the main program, we want to use a small learning rate, alpha 0.1. For a gamma, something like 0.9. Of course, the gamma is the discount factor. It's debatable whether or not you need it here. So discounting in general is used when you don't know you don't know for certain you're going to get some reward in the future, so it doesn't make sense to give it 100% weight. You could just as easily here use a 1.0 because the state transition functions in the cart pole example are deterministic as far as I'm aware. If I'm wrong, please someone correct me. And of course, the epsilon, for the epsilon greedy, we're going to start out at 1.0. You'll see why here in a second. And so you need to construct the set of states, which of course just corresponds to the integer representations of our continuous space. So you just have ranges from 0 to 9, and you construct a 4 vector out of that, right? So you have 0, 0, 0, 1, 1, 1, etc., etc., etc. And initialize your Q function. Here I'm going to initialize everything as 0, right? Recall that we could initialize it arbitrarily, but for the terminal states, you want that to be 0 because, again, the value of the terminal state is 0, and A is 2 in a range of 2 because we only have 2 actions, move left, move right. Whoops. Also, I'm going to run 50,000 games. If you have a slower computer, you might want to run fewer. It takes quite a bit of time to run. And I'm going to track the total rewards as we go along. So just a little helper line here to print out the number of games you're playing. It's always good to know where you are, right? If it stops chugging along, you want to know if it's broken or actually doing something useful. So you get your initial observation by resetting the environment, get your state, and calculate a random number. And so you take a maximum action if the random number is less than 1 minus epsilon. So epsilon is starting out at 1. So if random is less than 0, otherwise randomly sample your action space. Done flag to false, and your rewards for the episode is 0. Then you loop over the episode until you're done, and you go ahead and take the action A, getting your reward and the new observation. The state prime then is going to be get state of the observation, right? Because observation is a 4-vector of continuous numbers that we had to transform into a set of discrete integers, a 4-vector of discrete integers. Then we go ahead and calculate another random number and choose another action based upon that. Then calculate, sum up the total rewards and update the Q function based on the update rule I gave you in the slides. And of course, set the state and action to the S prime and A prime. And after each episode, you're going to decrease epsilon because you want this to, you don't want the epsilon to be permanently 1, right? You want to encourage some amount of exploration and some amount of exploitation, so epsilon has to be a function of time. And just save your total rewards. When it's all done, it's going to go ahead and plot it out. And you should see something similar to the following. I'm going to go ahead and run that now. And that is going to take a minute to run. And so here you have the output of the SARSA algorithm after running 50,000 iterations. So what you see is, first of all, a messy plot. That's to be expected with 50,000 games when you're plotting every single point. But what you notice immediately is that there's a general trend upward. And when epsilon reaches its minimum, epsilon goes to 0 and it does a fully exploitative strategy, the algorithm actually does a really good job of hitting 200 moves most of the time. Recall that 200 moves is the maximum number of steps for the cart pull problem, because good algorithms can get it to balance pretty much indefinitely, so it would never terminate. So the OpenAI Gym just terminates at 200 steps, so anything close to that is pretty good. Now, one thing that's interesting is that it does have a fair amount of variability. It doesn't actually balance it 200 moves the entire time, and there are a number of reasons for this. Perhaps you can speculate below. I invite you to speculate. My thought process is that the way we have discretized this space isn't sufficient to characterize the problem in such a way that the algorithm can learn something completely and totally useful. So it just doesn't have enough information based on the 10,000 states we've discretized it into. And there could be other things that matter. You could have other features, for instance, combinations of velocities and positions that matter. So we could have under-engineered the problem slightly, but for just a quick little chunk of 170 lines of code or so, it's actually quite good. So any questions, be sure to leave them below. And hey, if you've made it this far and you haven't subscribed, please consider. I'm going to be releasing more and more content like this. I'm doing this full time now. And I look forward to seeing you all in the next video. Oh, and by the way, in the next video, we're going to be taking a look at double Qlearning, which is yet another variation of these model-free bootstrap methods. See you then. Oh, and one other thing. If you want the code for this, I'll leave the link to my GitHub. This is code for my course, Reinforcement Learning in Motion. I'm just showcasing it here to show what you're going to learn in the course. So go ahead and click the link in the description, and it'll take you to my GitHub where you can find that code as well as all the code from the course. Hope you like it. See you guys in the next video. Welcome back, everybody, to Machine Learning with Phil. I am your host, Dr. Phil. In yesterday's video, we took a look at SARSA in the OpenAI Gym, getting the cart pull to balance itself. As promised, today we are looking at the algorithm of double Qlearning, also in the cart pull OpenAI Gym environment. So we had touched on Qlearning many months ago, and the basic idea is that Qlearning is a model-free, bootstrapped, off-policy learning algorithm. What that means is model-free. It does not need the complete state transition dynamics of the environment to function. It learns the game by playing it. Bootstrapped in that it doesn't need very much help getting started. It generates estimates using its initial estimates, which are totally arbitrary except for the terminal states. Off policy, meaning that it is using a separate policy other than it is using a behavioral policy and a target policy to both learn about the environment and generate behavior respectively. Now, when you deal with algorithms that take a maximizing approach to choosing actions, you always get something called maximization bias. So say you have some set of states with many different actions such that the action value function for that state and all actions is 0, then the agent's estimate, the Q, capital Q of S and A, can actually be will actually have some uncertainty to it, and that uncertainty is actually a spread in the values, right? And that spread causes it to have some amount of positive bias. And the max of the true values is 0, but the max of the capital Q, the agent's estimate, is positive. Hence, you have a positive bias, and that can often be a problem in reinforcement learning algorithms. So this happens because you're using the same set of samples to determine the maximizing action as well as the value of that action. And one way to solve this problem is to use two separate Q functions to determine the max action and the value, and you set up a relationship between them, and then you alternate between them as you play the game. So you're using one of them to determine the max action, one of them to determine its value, and you alternate between them so that you eliminate the bias over time. That's double Qlearning in a nutshell. The algorithm is the following. So you initialize your alpha and your epsilon, where alpha is your learning rate, epsilon is what you use for epsilon greedy. You want to initialize the Q1 and Q2 functions for all states and actions in your state and action space. Of course, that's arbitrary except for the terminal states, which must have a value of 0. And you loop over your set of episodes and you initialize your state, and for each episode, right, each step within the episode, choose an action from using your state, using an epsilon greedy strategy in the sum of Q1 and Q2. So you have the two separate Q functions. So if you're using single Qlearning, you would take the max action over just one Q, but since you're dealing with two, you have to account for that somehow, right? You could do a max, you could do a sum, you could do an average. In this case, we're going to take the sum of the two Q functions, take that action, get your reward, observe the new state, and then with the 0.5 probability, either update Q1 or Q2 according to this update rule here. And of course, at the end of the step, go ahead and set your state to the new state and keep looping until the game is done. So clear as mud? I hope so. By the way, if you want more reinforcement learning content, make sure to subscribe, hit the bell icon so you get notified. Let's get to it. So next up, we have our code. And here we are inside of our code editor. Again, I'm using Visual Studio Code to take a look at our double Qlearning script. I'm not going to be typing into the terminal. I think that's probably a little bit annoying. I'm just going to review the code as we go along. If you have seen my video on the SARSA algorithm, there's going to be a fair amount of overlap because we're solving the same set of problems over again. The only real difference is in that video we use SARSA to calculate the action value function, and in this case we're using double Qlearning. Again, we have a max action function. What this does is tells us the max action for a given state. To construct that, you make a numpy array out of a list that is for a given state, both actions. And as we said in the video, we're going to take the sum of the Q1 and Q2 for a given state for both actions. You want to take the argmax of that, and recall in numpy, the argmax function, if there is a tie, returns the first element. So if the left and right actions both have identical action value functions, then it will return the left action consistently. That may or may not be a problem, it's just something to be aware of. And once again, we have to discretize the spaces. Recall that the cart pole problem, which is just the cart sliding along a track with a pole that must be maintained vertically, right? In the cart pole example, we have a continuous space. The x and the theta can be any number within a given range, and likewise for the velocities. To deal with that, we have a couple options. We could simply use neural networks to approximate those functions, but in this case we're going to use a little trick to discretize the space. So we're going to divide it up into 10 equal chunks, and any number that falls within a particular chunk will be assigned an integer. So you'll go from a continuous to a discrete representation of your 4 vector, the observation. Along with that comes a get state function that you pass in the observation, and it just uses those digitized spaces. Just uses those linear spaces to use the numpy digitize function to get the integer representation of the respective elements of your observation. I've also added a function to plot the running average here. I do this because in the SARSA video we ended up with a little bit of a mess with 50,000 data points. This will plot a running average over the prior 100 games. Next up, we have to initialize our hyperparameters. Our learning rate of 0.1, this just controls the step size in the update equation. The gamma is of course the discount factor that the agent uses in its estimates of the future rewards. So I don't believe this should actually be 0.9. I left it here because it's not super critical. As far as I'm concerned, it should really be 1.0, and the reason is that the purpose of discounting is to account for uncertainties in future rewards. If you have some sequence of rewards with a probability of receiving them, then it makes no sense to give each of those rewards equal weight because you don't know if you're going to get them. In the cart pull example, the rewards are certain. As far as I'm aware, the state transition probabilities are 1. You know that if you move right, you're going to actually end up moving right, and you know deterministically where the pull and the cart are going to move. So it shouldn't be discounted as far as I'm concerned. Epsilon is just the epsilon factor for our epsilon greedy algorithm, and that's pretty much it for hyperparameters of the model. Next up, we have to construct our state space. So what this means, baby's unhappy. The state space is, of course, the representation of the digitized space. So we're going to have, for the cart position, you're going to have 10 buckets, the velocities 10 buckets, and likewise for the thetas, theta position and theta velocity. So you're going to have 10 to the 4 possible states. So 10,000 states, and those are going to be numbered all the way from 000 to 9999. That's all we're doing here is we're constructing the set of states. Next up, we have to initialize our Q functions. Recall that the initialization is arbitrary except for the terminal state, which must have a value of 0. The reason for this is that the terminal state, by definition, has a future value of 0 because you stop playing the game, right? Makes sense. You could initialize this randomly. You could initialize it with -1, +1. Doesn't really matter so long as the terminal state is 0. For simplicity, I'm initializing everything at 0. I'm going to play 100,000 games. The reason is that this algorithm eliminates bias, but at the expense of convergent speed. So you have to let it run a little bit longer. An array for keeping track of the total rewards. And we're going to loop over 100,000 games, printing out every 5,000 games to let us know it's still running. Always want to reset your done flag, your rewards, and reset the episode at the top. And you're going to loop over the episode, getting your state, calculating a random number for your epsilon greedy strategy. You're going to set the action to be the max action of Q1 and Q2 if the random number is less than 1 minus epsilon. Otherwise, you're going to randomly sample your action space. In any event, you take that action, get your new state, reward, and done flag, and go ahead and tally up your reward and convert that observation to a state S prime. Then go ahead and calculate a separate random number. The purpose of this random number is to determine which Q function we're going to update. We're going to be using 1 to calculate, we're alternating between them because we have to eliminate the maximization bias, right? 1 is for finding the max action, 1 is for finding the value of that action. We alternate between episodes by way of this random number. In both cases, you want to calculate the max action, either Q1 or Q2, and use the update rule I showed you in the slides to update the estimates for Q1 and Q2. And as you go at the end of the step, you want to reset the old observation to the new one, so that way you can get the state up here. And at the end of the episode, you want to go ahead and decrease epsilon. If you're not familiar with this, epsilon greedy is just a strategy for dealing with the explore-exploit dilemma. So an agent always has some estimate of the future rewards based on its model of the environment or its experience playing the game, if it's model-free or a model problem. Right, it can either explore or exploit its best known action. So one way of dealing with the dilemma of how much time should you spend exploring versus how much time should you spend exploiting is to use something called epsilon greedy, meaning that some percentage of the time you explore is some percentage of the time you exploit. And the way that you get it to settle on a greedy strategy is to gradually decrease that exploration parameter epsilon over time. And that's what we're doing here. And of course, you want to keep track of the total rewards for that episode. And recall, in the cart poll example, the agent gets a reward of +1 every time the pole stays vertical. And so every move that it doesn't flop over, it gets 1 point. And at the end, you're going to go ahead and plot your running averages. So I'm going to go ahead and run that. And that'll take a minute. While it's running, I want to ask you guys a question. So what type of material do you want to see? From what I'm seeing in the data, the reinforcement learning stuff is immensely popular. My other content, not so much, so I'm going to keep focusing on this type of stuff. But are you happy seeing the Sutton and Bardo type introductory material, or do you want to see more deep learning type material, right? There's a whole host of dozens of deep reinforcement learning algorithms we can cover. But I'm actually quite content to cover this stuff because I believe that if you can't master the basics, then the deep learning stuff isn't going to make sense anyway, right? Because you have the complexity of deep learning on top of the complexity of the reinforcement learning material on top of it. So if there's anything in particular you guys want to see, make sure to leave a comment below. And hey, if you haven't subscribed and you happen to like reinforcement learning and machine learning material, please consider doing so. If you liked the video, make sure to leave a thumbs up. Hey, if you thought it sucked, go ahead and leave a thumbs down and tell me why. I'm happy to answer the comments, answer your objections, and if you guys have suggestions for improvement, I'm all ears. And here we are, it is finally finished with all 100,000 episodes. And you can see here the running average over the course of those games. As you would expect, the agent begins to learn fairly quickly, balancing the cart pull more and more and more. By about 60,000 games, it starts to consistently hit the 200 move threshold, where it is able to balance the cart pull all 200 moves of the game. Now recall this was with a gamma of 1.0. I'm going to go ahead and rerun this with a gamma of 0.9 and see how it does. So burn this image into your brain, and I'm going to go ahead and check it out with a gamma of 0.9 and see if we can do any better. And we are back with the second run using a gamma of 0.9, and you can see something quite interesting here. So it actually only kind of ever reaches the 200 mark just for a handful of games, and then kind of stutters along, actually decreasing in performance as it goes along. So something funny is going on here, and to be frank, I, off the top of my head, am not entirely certain why. So I invite you all to speculate. However, what's also interesting is that this is the second time I'm recording this. I recorded it earlier and didn't scroll down the code, so you ended up staring at the same chunk of stuff, had to redo it. And in that case, I had a gamma of 0.9 as well, and it seemed to work just fine. So I suspect there's some significant variation here to do with the random number generator. And it could just all be due to that, right? This is a complex space, and it wanders around different portions. This could happen potentially because it doesn't visit all areas of the parameter space enough times to get a reasonable estimate of the samples, and there may be some type of bias on where it visits later on in the course of the episodes, although that sounds kind of unlikely to me. But either way, that is double Qlearning. You can see how the hyperparameters actually affect the model, and it seems to have a fairly large effect, as you might expect. In the next video, we're going to be taking a look at double SARSA. So if you are not subscribed, I ask you to please consider doing so. Hit the notification icon so you can see when I release that video. And I look forward to seeing you all in the next video. Well, I hope that was helpful, everyone. So what did we learn? We learned about Qlearning, policy gradient methods, SARSA, double Qlearning, and even how to create our own reinforcement learning environments. This is a very solid foundation in the topic of reinforcement learning, and you're pretty well prepared to go out and explore more advanced topics. So what are those more advanced topics? So right now the forefront are things like deep deterministic policy gradients, which is, as you might guess from the name, a more advanced version of policy gradient methods. There are also actor-critic methods, behavioral cloning. There's all sorts of more advanced topics out there that you're now pretty well equipped to go explore. These are particularly useful in environments where you have continuous action spaces. So all the environments we studied in this set of tutorials have a discrete action space, meaning the agent only moves or takes some discrete set of actions. Other environments, such as the bipedal walker, car racing, things of that nature, have continuous state spaces, continuous action spaces, which require different mechanisms to solve. Qlearning really can't handle it. So you're now free to go ahead and check that stuff out. If you made it this far, please consider subscribing to my channel, Machine Learning with Phil. And I hope this is helpful for all of you. Leave a comment down below and make sure to share this. And I'll see you all in the next video.